What if I told you that one of Earth's most vital defenses, something we never see but rely on every single day, was once disrupted by an event so powerful it came from beyond our solar system? Picture this, a day when compasses spun wildly, auroras danced in skies where they shouldn't, and satellites faltered, not because of the sun's fury, but because of a cosmic whisper from a dead star millions of light years away. This isn't science fiction. It's a real phenomenon that scientists have traced back to an outburst from a neutron star, a remnant of a supernova so dense, a single teaspoon of its material would weigh 1 billion tons. And for a brief, eerie moment, that distant corpse of a star reached across the universe and tugged at Earth's magnetic field, our planet's invisible force field against the chaos of space. We often think of space as silent and empty, but the truth is far more thrilling. The cosmos is alive with invisible forces, and Earth's magnetic field is our quiet guardian, deflecting solar winds and cosmic rays that would otherwise strip away our atmosphere. But what happens when something out there, something unimaginably powerful, decides to knock on our door? That's the story we're unraveling today, the day a dead star interrupted Earth's magnetic field. It's a tale that begins in the heart of a collapsed star, travels through the void, and ends with a ripple in the very forces that protect us. And the most fascinating part: this isn't just a relic of the past. Scientists warn it could happen again. So how does a star that's already died manage to reach out and touch us? To understand that, we'll dive into the mind-bending physics of neutron stars, objects so strange they defy everything we know about matter. We'll explore how their eruptions, known as magnetar flares, can unleash energy equivalent to 1 billion suns in milliseconds. And most importantly, we'll uncover what this means for us. Could a future outburst be stronger? Could it temporarily cripple our technology or even pose risks to life? The answers lie in the delicate dance between Earth's magnetic field and the unpredictable giants lurking in the darkness of space. So buckle up, we're about to journey into one of the universe's most extraordinary mysteries, where the line between distant stars and our daily lives is thinner than you've ever imagined. To grasp how a dead star could reach across the cosmos and nudge Earth's magnetic field, we need to wrap our minds around neutron stars, nature's most extreme physics experiments. Imagine crushing an entire star, twice the mass of our sun, into a sphere no wider than Manhattan. The result is an object so dense, a single sugar cube of its material would outweigh Mount Everest. This isn't just hypothetical. When massive stars exhaust their fuel, they don't fade quietly. They explode in supernovas so violent, they outshine entire galaxies for weeks. What's left behind isn't just a corpse. It's a neutron star, a spinning, magnetized relic where the rules of gravity and magnetism get rewritten. The real marvel lies in their magnetic fields. While Earth's magnetic field is strong enough to guide compass needles, a neutron star's field can be a quadrillion times more powerful, enough to atomize your DNA from thousands of miles away. Some neutron stars, called magnetars, take this to another level. Their magnetic fields are so intense, they occasionally crack under the strain, releasing flares of energy in milliseconds that rival the sun's output over centuries. And here's where things get eerie for Earth. In 2004, astronomers detected one such flare from a magnetar 50,000 light-years away. For a fraction of a second, it outshone the full moon in gamma rays, and though it lasted just 1/10 of a second, its energy rippled through our solar system, briefly rattling Earth's upper atmosphere and triggering sensors normally reserved for solar storms. But how does something so distant affect us? The answer lies in the invisible threads connecting the cosmos. Magnetar flares don't just emit light, they blast out waves of charged particles and electromagnetic disturbances. When these waves encounter Earth's magnetic field, they can induce electric currents in our planet's crust, like a cosmic version of static shocking your fingertips after walking on carpet. Normally, our magnetic field shrugs off solar wind and cosmic rays, but a close-range magnetar flare could overwhelm it, inducing currents strong enough to disrupt power grids, scramble satellite communications, or even create phantom auroras near the equator. What makes neutron stars uniquely threatening isn't just their power, it's their unpredictability. Unlike the Sun, which follows an 11-year cycle of activity, magnetars erupt without warning. And while the 2004 event was harmless, astronomers have catalogued older flares in our galaxy's history that were thousands of times stronger. If one of those erupted nearby, the consequences could range from mesmerizing skies lit by global auroras to catastrophic with potential blackouts lasting months. The chilling truth: we'd have no advance warning. The flare's light and its electromagnetic effects would arrive at the same time, giving us 0 seconds to prepare. This brings us to the heart of the mystery. Neutron stars remind us that the universe isn't just vast, it's volatile. Their existence forces us to confront a humbling reality. Earth's magnetic field, for all its might, is just a fragile bubble in a cosmos teeming with forces beyond our control. And sometimes those forces decide to knock. The death of a massive star isn't just an ending, it's a transformation into one of the universe's most extreme objects. When a star many times heavier than our Sun burns through its nuclear fuel, the delicate balance between outward pressure and inward gravity shatters. In an instant, the star's core collapses, falling in on itself at nearly a quarter the speed of light. The outer layers, suddenly without support, rebound off this collapsing core in a cataclysmic explosion, a supernova so bright it can outshine an entire galaxy. But the real marvel isn't the explosion itself. It's what remains: a neutron star, a city-sized cinder packing more mass than our Sun into a sphere barely 12 miles across. This isn't just dense matter, it's matter pushed to its absolute limit. Under such unimaginable pressure, electrons and protons are crushed together, merging into neutrons. The result is a material so compact, a single teaspoon would weigh 6 billion tons on Earth. To put that in perspective, that's like squeezing the entire human population into a sugar cube. But the star's violent birth does something even more extraordinary. It twists and amplifies its magnetic field to strengths that defy intuition. As the core collapses, the same physics that makes a figure skater spin faster when pulling in their arms applies to the star's magnetic field. What was once a modest stellar magnetic field gets compressed and supercharged, reaching intensities up to a quadrillion times stronger than Earth's. This process creates cosmic powerhouses known as magnetars, neutron stars with magnetic fields so intense they're essentially universe-scale electromagnets. Their magnetic energy isn't just strong, it's volatile. Like a coiled spring under too much tension, these fields occasionally snap, releasing bursts of gamma rays and X-rays in milliseconds that outshine entire galaxies. And here's where things get eerie for Earth. These outbursts don't just vanish into space. They send shock waves of charged particles and electromagnetic disturbances rippling across light years, capable of brushing against our planet's magnetic field like a cosmic hand tapping on a window. The implications are staggering. A magnetar's magnetic field isn't just a static force, it's a dynamic, writhing entity that can reconfigure itself in instants. When these stars experience starquakes, cracks in their rigid crusts caused by magnetic stress, they release energy equivalent to 1 billion hydrogen bombs. Some of these events, like the gamma-ray flare from Magnetar SGR 1820-20 in 2004, have been detected halfway across our galaxy, their energy briefly distorting Earth's ionosphere. It's a humbling reminder that even in death, stars retain the power to reach across the cosmos and remind us of our place in an ever-changing universe. What makes neutron stars so fascinating isn't just their extreme physics, it's how they force us to rethink the nature of matter itself. Under their crushing gravity, atoms cease to exist in any recognizable form. Protons and electrons merge into neutrons, creating a bizarre quantum fluid where matter behaves more like a single gigantic nucleus than anything we've ever seen on Earth. And yet, these exotic objects aren't just cosmic curiosities. They're active participants in the universe, capable of influencing worlds light years away. Their magnetic fields don't just affect their immediate surroundings. They can stretch across interstellar space, leaving fingerprints on planets they've never touched. This brings us to a profound realization. The birth of a neutron star isn't just a distant spectacle, it's the creation of a cosmic time bomb, ticking quietly in the darkness. Some of these objects will spend millennia silently spinning down, their magnetic fields slowly fading. Others might unleash their pent-up energy without warning, sending pulses of radiation through the galaxy that could momentarily disrupt the delicate systems we rely on. And while the odds of a direct hit are slim, the very existence of these stellar remnants reminds us that Earth doesn't orbit in isolation. We're part of a dynamic, interconnected cosmos where events half a galaxy away can still whisper to us across the void. The magnetic fields around neutron stars aren't just strong. They rewrite the rules of physics as we know them. Picture the strongest magnet you've ever encountered, maybe one that can lift a car. Now amplify that by 1 trillion times, and you're still nowhere close to the sheer force radiating from a neutron star. These cosmic powerhouses generate fields so intense, they can bend the paths of atoms and distort the very fabric of space around them. But here's what's truly mind-blowing. These fields don't just sit there, they spin. When a neutron star rotates sometimes hundreds of times per second, its magnetic field whips through space like a lighthouse beam, slicing through the cosmos with precision. If that beam happens to sweep across Earth, we detect it as a pulse of radiation, earning these stars their nickname, pulsars. But not all neutron stars are content to simply blink in the darkness. Some, known as magnetars, take magnetic fury to another level. Their fields are so twisted and unstable, they occasionally snap like an overstretched rubber band, unleashing flares of energy in milliseconds that outshine our sun for years. So how does a burst from one of these magnetars cross the unimaginable void to touch Earth? It all comes down to the invisible highways of the universe, magnetic field lines. Just as Earth's magnetic field stretches far beyond our atmosphere, a magnetar's field extends light years into space, weaving through the interstellar medium like an invisible web. When a starquake or magnetic reconnection triggers a flare, it sends shockwaves rippling along these field lines, accelerating particles to near light speed. These particles, along with an accompanying blast of X-rays and gamma rays, race outward in all directions. By the time this energy reaches us, it's been diluted by distance, but not entirely harmless. In 2007, a magnetar flare 50,000 light-years away was powerful enough to ionize Earth's upper atmosphere, disrupting radio communications globally for nearly an hour. What's startling is how little it takes. A similar outburst from a magnetar just 10 light-years away could deliver a blow equivalent to a solar superstorm, potentially frying satellites and overloading power grids. The real question isn't whether these cosmic bullets can reach us, it's how close one needs to be to cause real damage. The terrifying beauty of magnetars lies in their unpredictability. Unlike solar flares, which we can track as they build, magnetar bursts give no warning. One moment, the star is silent. The next, it's hurling enough energy into space to power human civilization for billions of years. And while the odds of a direct hit are astronomically low, the universe has a way of reminding us that rare doesn't mean impossible. Every now and then, a dead star whispers to us across the light years, not with light, but with the invisible hand of magnetism, proving just how connected we truly are to the cosmos. Magnetars aren't just theoretical oddities, they've already left their mark on Earth. One of the most striking examples happened in 1998, when a satellite designed to monitor gamma rays suddenly detected a surge of energy from deep space. The source, a magnetar 20,000 light-years away in the constellation Aquila. For a fraction of a second, this dead star released more energy than our Sun will emit in 100,000 years. The burst was so intense, it temporarily blinded sensors on multiple spacecraft and even caused detectable disturbances in Earth's ionosphere, the electrically charged layer of our upper atmosphere. But that wasn't an isolated event. Fast forward to 2004 and another magnetar, this one 50,000 light-years away in the constellation Sagittarius, unleashed a flare so powerful. Its gamma-ray spike outshone the full moon despite originating halfway across our galaxy. For a tenth of a second, it was the brightest gamma-ray source in the sky, even visible to telescopes in broad daylight. What's chilling is how these outbursts ripple through space. The energy doesn't just travel as light, it warps the surrounding magnetic fields like a stone tossed into a pond, creating waves of charged particles that can nudge Earth's own magnetic shield when they pass by. Scientists have even found evidence of far more ancient encounters. Buried in tree rings and ice cores are traces of radioactive isotopes like carbon-14 and beryllium-10, telltale signs of intense cosmic radiation striking our planet. One spike, dated to around 774 AD, was so significant, researchers initially thought it came from a supernova, but the more they studied it, the stranger it looked. The radiation profile matched something far rarer, a magnetar flare. If a similar event occurred today, the consequences could range from dazzling global auroras visible even at the equator to disruptive, with potential satellite malfunctions and power grid fluctuations. The unsettling truth is that we're only beginning to understand how vulnerable Earth might be to these cosmic outbursts. In 2019, astronomers detected a magnetar flare from a galaxy 13 million light-years away, proof that these events aren't confined to our Milky Way. And while distance usually protects us, the sheer scale of magnetar energy means even a moderately close one, say, within 10 light-years, could deliver a punch comparable to the worst solar storm in recorded history. The difference, unlike solar storms which give us days of warning, a magnetar flare would arrive at the speed of light, leaving zero time to prepare. What makes these discoveries so gripping isn't just the raw power of magnetars, it's how they redefine our understanding of cosmic hazards. We've long known about asteroids and solar flares, but magnetars remind us that the universe holds surprises we're only starting to catalog. Every flicker of gamma rays from deep space is a message in a bottle, telling us that the cosmos is far from quiet, and that Earth, for all its isolation, isn't entirely out of reach. Earth's magnetic field is far more than just a guide for compass needles. It's a dynamic, living shield, constantly flexing and flowing in response to forces both within and beyond our planet. Picture it like an invisible force field generated by the churning of molten iron in Earth's outer core. This swirling sea of metal acts like a colossal electromagnet, producing a field that stretches tens of thousands of miles into space, deflecting charged particles from the solar wind and cosmic rays that would otherwise strip away our atmosphere. Without it, our planet might resemble Mars, a barren, airless world where life as we know it couldn't survive. But this shield isn't invincible. When the 2004 Magnetar flare struck, it delivered a subtle but undeniable reminder of our cosmic vulnerability. Though the eruption originated 50,000 light-years away, its gamma-ray burst was powerful enough to briefly ionize atoms in our upper atmosphere, creating a temporary layer of charged particles. Normally, Earth's magnetic field absorbs or redirects such disturbances, but this event proved that even distant stellar corpses can send ripples through our protective bubble. What's startling is how narrowly we avoided more serious effects. Had that Magnetar been just a few thousand light-years closer, the surge of energy could have induced powerful electrical currents in the ground, potentially overloading power grids, disrupting satellites, or even scrambling communication networks. This raises a critical question: how much stress can Earth's magnetic field handle before it buckles? The answer lies in its structure. Unlike a rigid bar magnet, our planet's field is fluid and ever-changing, with strength that varies by location. At the poles where field lines converge, it's robust enough to deflect most solar radiation. Near the equator, however, the field is weaker, creating regions like the South Atlantic anomaly, a zone where satellites often experience glitches due to increased radiation exposure. A powerful enough Magnetar flare could exploit these vulnerabilities, temporarily compressing or even puncturing our magnetic shield in localized areas. History offers clues about what could happen under extreme conditions. The Carrington event of 1859, a solar storm so intense it set telegraph wires ablaze, showed how geomagnetic disturbances can induce currents in human infrastructure. But a Magnetar flare could dwarf even that. Computer simulations suggest a nearby outburst might not just distort our magnetic field, it could generate ground currents strong enough to melt transformers, leaving entire continents without power for months. The real wild card: we wouldn't see it coming. Unlike solar storms, which take days to reach us, a magnetar's gamma rays and magnetic pulses arrive at light speed, giving zero warning. Yet for all its fragility, Earth's magnetic field has an ace up its sleeve: resilience. Over geological time, it's weathered countless solar storms and cosmic bombardments, even reversing polarity entirely every few 100,000 years. This adaptability hints that while a Magnetar flare might jostle our shield, it's unlikely to dismantle it entirely. Still, in a world increasingly reliant on delicate electronics, even a temporary magnetic hiccup could have cascading consequences, proof that in the grand cosmic dance, Earth's silent guardian isn't just a scientific curiosity. It's the thin blue line between civilization and chaos. Deep beneath our feet, in the churning heart of Earth's outer core, lies the engine powering our planet's invisible shield. A 3,000-kilometer thick layer of molten iron and nickel swirls in slow, turbulent currents, acting like a colossal dynamo. This rotating sea of liquid metal generates electric currents, which in turn produce Earth's magnetic field, a force that arcs from pole to pole, wrapping our world in a protective embrace. Think of it as a cosmic deflector shield, constantly pushing away the torrent of charged particles streaming from the sun and distant galaxies. Without this barrier, our atmosphere would slowly erode, stripped away by solar winds, just as Mars lost its own billions of years ago. But this shield isn't static. It breathes, fluctuates, and even flips polarity over millennia. Satellite measurements reveal it's currently weakening by about 5% per century, with some regions like the South Atlantic anomaly already so thin spacecraft passing through risk electronic malfunctions from increased radiation. This natural ebb and flow usually happens too slowly to impact daily life. However, when an external force like a magnetar's outburst tugs at this delicate system, the effects can ripple far beyond compass needles pointing awry. Here's where the dance between Earth's magnetic field and a dead star's fury gets fascinating. Magnetar flares don't just send radiation, they unleash tsunamis of magnetized plasma. When these waves collide with Earth's magnetic field, they don't simply bounce off. Instead, they transfer energy into our magnetosphere, compressing it on the day side and stretching it into a long tail on the night side. This distortion can induce electric currents in anything conductive: power lines, pipelines, even the ground itself. The results range from surreal auroras appearing over the equator to severe transformers overheating as rogue currents surge through grids. Historical records hint at what could happen under extreme stress. During the Carrington event of 1859, a solar storm so intense it supercharged telegraph lines, electrocuting operators, and setting paper ablaze proved how vulnerable human infrastructure is to magnetic disturbances. But a magnetar's punch could be far worse. Solar storms deliver their energy over hours, allowing some dissipation. A magnetar dumps its entire fury in milliseconds, creating a shockwave that might overwhelm Earth's defenses before they can react. Simulations suggest a nearby flare could temporarily create gaps in our magnetic field, allowing radiation normally deflected at the poles to pour into lower latitudes. Yet Earth's magnetic field has one critical advantage: flexibility. Unlike the rigid crust we walk on, the magnetosphere is fluid, redistributing stress like a rubber sheet absorbing a pebble's impact. This resilience has helped it survive billions of years of cosmic bombardment. But in our modern world, where a single grid failure can trigger cascading blackouts, the stakes are higher than ever. A magnetar's interference might not destroy our shield, but it could shake it just enough to remind us how much we rely on this silent, spinning guardian deep beneath our feet. And that's a humbling thought when gazing at the stars. Imagine a neutron star cosmic cannon capable of firing beams of energy so concentrated they could punch through the fabric of space itself. Now picture one of those beams, narrower than a pencil but packing the power of a supernova, aimed directly at Earth. In that instant, our planet's magnetic field wouldn't just bend, it would warp under pressure unlike anything the sun could produce. The impact wouldn't be uniform like a solar storm's broad brushstroke. Instead, it would hit like a scalpel, compressing the magnetosphere on one side while leaving the other untouched. This sudden asymmetry could twist the entire field out of shape, creating temporary weak spots where radiation normally deflected at the poles might spill through. The physics behind this disruption is both elegant and terrifying. A magnetar's energy beam doesn't just carry radiation, it's threaded with its own magnetic field, twisted into a helix as the star spins. When this corkscrew of force slams into Earth's magnetosphere, the two fields don't merge peacefully. They battle for dominance, with the magnetar's field temporarily overpowering ours in the impact zone. Think of it like pressing a thumb into a balloon. The surrounding material stretches thin, creating a dent where the pressure isn't balanced. For minutes or even hours, that dent could linger, a wound in our planetary shield. Distance is the critical factor here. A magnetar 10,000 light-years away might only give our upper atmosphere a light tap, as in 2004. But bring that same star within 1,000 light-years, and the effects escalate dramatically. The energy doesn't just weaken with distance, it follows the inverse square law, meaning a magnetar twice as close delivers 4 times the punch. At certain angles, a near-miss beam could still graze us with enough force to induce continent-wide electrical surges. like a lightning strike to the planet's nervous system. What makes this scenario uniquely unsettling is the unpredictability. Unlike solar storms where we can track sunspots and coronal mass ejections, a magnetar's beam gives no warning. One moment the sky is calm, the next satellites report gamma-ray spikes as the first particles breach our defenses. Power grids might experience mysterious voltage swings. High-frequency radio communications could cut out globally, not from solar interference, but because the ionosphere has been ionized unevenly, like a mirror shattered into fragments. Yet Earth's magnetic field has survived worse. Over eons, it's endured supernova, gamma-ray bursts, and even the slow erosion of our own weakening dynamo. A magnetar's strike wouldn't obliterate the field, just temporarily dent it. The real risk isn't annihilation, but asymmetry. A lopsided magnetosphere could funnel charged particles into new paths, creating auroras in daylight or exposing equatorial regions to radiation normally confined to the poles. For a civilization built on satellites and electronics, that distortion could be enough to rewrite the rules of our technological existence, at least until the field springs back into shape. The takeaway isn't doom but perspective. These events measure the resilience of the invisible forces protecting us. Every compass pointing north, every aurora dancing at the poles, they're proof of a shield that bends but rarely breaks. And when a dead star whispers across the light years, it doesn't just test our defenses. It reminds us how dynamic, how alive our quiet magnetic bubble truly is. A sudden lurch in Earth's magnetic field wouldn't just flicker lights. It would rewrite the rules of modern infrastructure. Picture transformers, those humming giants of the power grid, suddenly overloaded by electrical currents surging through the ground like invisible tidal waves. These currents, induced by rapid shifts in the magnetosphere, could heat copper coils until they melt, triggering cascading blackouts. Unlike localized outages from storms, this would unfold continent scale, with repair times measured not in hours but months, since replacing a fried transformer isn't like swapping a light bulb. Each unit weighs hundreds of tons and requires custom manufacturing. The chilling precedent, the Quebec blackout of 1989, where a solar storm took down the entire grid in 90 seconds. A magnetar's punch could dwarf that event. Satellites wouldn't fare any better. Orbiting beyond Earth's densest atmospheric layers, they rely on electronics hardened against routine solar radiation, not the gamma-ray deluge of a nearby stellar outburst. Sensitive components could fry mid-orbit, silencing GPS signals, weather monitoring, and global communications. The International Space Station, shielded by Earth's magnetic field only part-time, might become a deadly trap. Astronauts caught outside during a surge would absorb a year's worth of radiation in milliseconds, risking acute sickness or worse. Even shielded, the station's systems could glitch from induced currents, like the phantom commands that plagued satellites during the 2003 Halloween solar storms. Then there are the skies. Auroras, normally confined to polar latitudes, might ignite over Jakarta and Nairobi as charged particles slip through weakened magnetic zones. While dazzling, these light shows would signal deeper chaos. The ionosphere, a critical layer for bouncing radio signals, would ripple like a disturbed pond. High-frequency communications, from aviation to emergency broadcasts, could cut out globally, but the strangest effect might be underground. Pipelines, acting as unintended conductors, could corrode at accelerated rates as stray currents seek paths of least resistance. After the solar storm of 1972, engineers found sections of Alaskan oil pipes had corroded 10 times faster than normal, etched by invisible forces from space. The long-term implications stretch beyond hardware. Imagine months without stable power grids, hospitals running on generators, water treatment plants offline, supply chains crumbling. Unlike natural disasters that strike one region, this would be a simultaneous global test of resilience. Financial systems relying on timestamp transactions might falter if satellite clocks desynchronize. Even agriculture could suffer. Some studies suggest cosmic rays influence cloud formation, potentially altering rainfall patterns after a major magnetic disturbance. Yet the most profound impact might be psychological. For the first time, humanity would viscerally grasp its dependence on an invisible shield most never think about. A magnetar's nudge wouldn't just disrupt technology. It would reveal, in stark terms, how fragile our cosmic neighborhood truly is, and that realization could linger long after the lights come back on. The long-term environmental consequences of a weakened magnetic field stretch far beyond flickering lights and satellite glitches. They could rewrite the very chemistry of life on Earth. Without the full strength of our planetary shield, cosmic rays that normally deflect harmlessly into space would penetrate deeper into the atmosphere. These high-energy particles don't just pass through air, they smash into nitrogen and oxygen molecules, triggering cascades of secondary radiation. Over months or years of sustained exposure, this invisible rain could alter DNA replication rates in plants and animals, accelerating mutations in ways unseen since prehistoric radiation spikes. Scientists have already observed this phenomenon on a smaller scale. Flight crews and astronauts who experience higher radiation exposure at altitude show measurable increases in chromosomal abnormalities. Now imagine that effect magnified across entire ecosystems. The ozone layer would face its own silent battle. Cosmic rays colliding with atmospheric molecules produce nitrogen oxides, compounds known to chew through ozone. During solar storms, we've seen temporary ozone depletion over the poles, but a prolonged magnetic disturbance could thin this protective blanket globally. The result, a surge in ultraviolet radiation reaching the surface, with consequences ranging from increased skin cancer rates to disrupted phytoplankton populations, the microscopic engines driving ocean food chains. Historical parallels exist. Fossil records suggest similar UV spikes may have contributed to minor extinction events, leaving behind telltale traces like malformed pollen grains in ancient rock layers. Yet nature has weathered worse. Life's resilience shows in places like Chernobyl's exclusion zone, where radiation-resistant organisms now thrive. The real intrigue lies in how future scientists might detect such an event in our geological record. Unlike asteroid impacts that leave iridium-rich dust layers, a magnetic disturbance would imprint itself subtly through spikes in radioactive isotopes like beryllium-10 in ice cores, or sudden shifts in the fossilized magnetic orientations of iron-rich sediments. Even tree rings could bear witness. Years of stunted growth coinciding with increased carbon-14 levels would paint a vivid portrait of atmospheric chaos. The most fascinating evidence might come from humanity's own artifacts. Future archaeologists studying our era could uncover strange anomalies, electronic devices with crystalline structures altered by radiation, or layers of sediment unusually rich in rare metals scavenged from fried electronics. Our technological civilization, it turns out, might leave the clearest fingerprints of all. These clues would tell a story not of fiery impacts or volcanic winters, but of a silent, invisible crisis, one where the sky itself briefly forgot to protect us. Detecting such an event today would require a symphony of instruments working in unison. Magnetometers worldwide would record the initial field distortion, while gamma-ray telescopes like NASA's Swift satellite would pinpoint the culprit magnetar's location. More subtle effects like atmospheric chemistry changes would emerge from ozone monitoring satellites and ground-based LiDAR stations tracking particle densities. The real challenge would be connecting these disparate signals into a coherent narrative, especially if the magnetar itself remains obscured by interstellar dust. What makes this detective work so critical isn't just academic curiosity, it's preparedness. By understanding how past magnetic disturbances left their mark, we gain clues about what to monitor during future events. Networks of radiation sensors, deep-sea sediment samplers, and even citizen science projects tracking mutation rates in local wildlife could form an early warning web. After all, the next cosmic whisper might not be a faint echo from 50,000 light-years away, but a shout from far closer, one we can't afford to miss. Spotting a neutron star's outburst before it reaches Earth isn't just about having the right tools. It's about listening to the universe in a language of invisible light. When a magnetar crackles to life, its first scream isn't visible to our eyes. It arrives as a torrent of X-rays and gamma rays, high-energy photons that pierce through interstellar dust like searchlights in the cosmic dark. This is where instruments like NASA's Fermi Gamma Ray Space Telescope become our interstellar sentinels. Orbiting high above Earth's atmosphere, which blocks these dangerous wavelengths, Fermi's Large Area Telescope scans the entire sky every 3 hours, its sensors fine-tuned to catch the telltale spike of a magnetar's fury. The detection process resembles catching a bullet in midair. While blindfolded, only the bullet travels at light speed, and the blindfold is the incomprehensible vastness of space. When Fermi spots a gamma-ray burst, supercomputers within seconds triangulate its origin using timing differences as milliseconds between detectors. This rapid response is crucial. While the light from a magnetar flare and its electromagnetic effects arrive simultaneously, knowing the burst's direction and strength allows scientists to predict which planets or spacecraft might bear the brunt. During the 2004 event, this system pinpointed the flare's source within the Sagittarius constellation, confirming it came from well outside our solar neighborhood. But Fermi isn't working alone. A global network of telescopes forms a cosmic early warning system. Europe's integral satellite specializes in gamma-ray spectroscopy, dissecting bursts to reveal their magnetic fingerprints. Japan's Hitomi spacecraft, before its tragic failure, demonstrated how X-ray polarimetry could measure the twisted magnetic fields within these eruptions. Even ground-based observatories play a role. When a gamma-ray burst ionizes Earth's upper atmosphere, radio telescopes can detect the resulting disturbances like sonar pings in an oceanic abyss. The real power lies in combining these observations with historical data. Ice cores from Antarctica show radioactive isotopes like beryllium-10 spiking around 774 A. While medieval tree rings reveal abnormal carbon-14 levels, both potential signatures of ancient magnetar strikes. By matching these terrestrial records with observations of nearby neutron stars, astronomers are piecing together a timeline of galactic violence. One startling discovery: magnetar flares powerful enough to leave earthly traces might occur every few thousand years in our cosmic backyard. So what are the odds of another major event in our lifetime? Statistically slim but not negligible. Current models suggest there's roughly a 1% chance per century of a magnetar flare strong enough to disrupt satellites occurring within 10,000 light-years. The probability drops to 1 in 10,000 for a Carrington-level event originating closer than 1,000 light-years. But statistics offer cold comfort when dealing with cosmic unpredictability. Magnetars don't follow schedules, and outliers exist like the bizarre Christmas burst of 2010, where an unknown neutron star flared repeatedly over 24 hours, defying all eruption models. This uncertainty fuels new detection strategies. Scientists are now training machine learning algorithms to comb through telescope data, hunting for subtle precursor signals, tiny starquakes or magnetic twitches that might hint at an impending outburst. Others propose neutrino detectors could provide split-second advance warning, as these ghostly particles sometimes escape a neutron star's crushing gravity slightly before light. Meanwhile, projects like the Deep Space Climate Observatory monitor Earth's magnetic field in real time, acting as a cosmic canary in the coal mine for incoming disturbances. The sobering truth is that perfect protection is impossible. Even with our most advanced systems, we'd have at best minutes between detection and impact, barely enough time to safeguard critical infrastructure. Yet every flare we catch, every isotope spike we analyze, sharpens our understanding of these celestial monsters. And in that knowledge lies our best defense, not against the magnetars themselves, but against the complacency of believing the cosmos will always play by our rules. Statistically speaking, the universe plays a cruel joke with probabilities. Events so rare they shouldn't happen in human lifetimes sometimes do, simply because the cosmos operates on timescales far beyond our own. When it comes to magnetar flares strong enough to jostle Earth's magnetic field, the numbers seem comforting at first glance. Perhaps one significant outburst every several thousand years within our galactic neighborhood, with the nearest known magnetar safely distant at over 9,000 light-years. But here's where the statistics get slippery. Our galaxy alone hosts an estimated 30 million neutron stars, and we've catalogued fewer than 30 confirmed magnetars. That's like judging an ocean's danger by studying a single tide pool. The real uncertainty lies in what we haven't seen yet. Take soft gamma repeaters, a class of magnetars that erupt unpredictably like cosmic geysers. Before 1979, astronomers didn't know they existed. Then one erupted so violently, its gamma-ray pulse saturated detectors across the solar system despite originating from another galaxy entirely. This revelation rewrote our understanding of cosmic threats overnight. Today, we know of magnetars with magnetic fields so strong, they could theoretically disrupt electronics from hundreds of light-years away. But we've only discovered these monsters because they happened to flare during our brief window of observation. How many more lurk unseen, their outbursts directed away from Earth or simply occurring in epochs before human records began? Preparing for such an edge case event is a paradox. On one hand, the odds are vanishingly small, comparable to being struck by lightning while winning the lottery. Yet we still install lightning rods and buy lottery tickets because consequences matter more than probabilities when the stakes are high. Modern space weather monitoring reflects this balance. Systems like NOAA Space Weather Prediction Center, designed for solar storms, could detect a magnetar flare's arrival within milliseconds, not to prevent it, but to diagnose its impact as it unfolds. Grid operators now routinely install capacitors to block geomagnetically induced currents, a defense that would also blunt some effects from a cosmic outburst. The most intriguing safeguards emerge from historical detective work. By studying isotope spikes in ancient ice and tree rings, scientists have reconstructed a timeline of extreme cosmic radiation events. One pattern stands out. The worst episodes cluster in periods when our solar system passed through dense spiral arms of the Milky Way, where neutron stars are more densely packed. We're currently cruising through a relatively sparse galactic neighborhood, buying us time, but in about 2 million years, we'll enter the perilous Orion Arm. While that timeline dwarfs human civilization, it underscores how cosmic danger fluctuates over epochs far longer than our recorded history. Perhaps the greatest vulnerability isn't technological, but psychological. Humanity tends to prepare for disasters it's experienced: hurricanes, earthquakes, solar storms. a magnetar's interference represents something stranger, a threat with no living memory, no cultural reference points. Unlike an asteroid impact, there'd be no fiery streak across the sky to signal danger, just silent, invisible forces twisting the instruments we depend on. That very invisibility makes it a challenge to take seriously, even as our dependency on fragile electronics grows. Yet in this uncertainty lies an odd reassurance. The same physics that makes magnetars terrifying also makes them fascinating laboratories. By studying how their energy propagates across light years, we're learning to harness magnetic fields here on Earth, from fusion reactors to medical imaging. Every flicker from these dead stars teaches us something new about the universe's extremes. So while we may never fully prepare for such a rare event, understanding it reshapes our relationship with the cosmos. Not as a static backdrop, but as a dynamic arena where even the ashes of long-dead stars can still whisper or shout across the void. Protecting our planet from cosmic threats isn't about building force fields or deflecting stellar bullets, it's about smart resilience. Imagine if every power grid transformer had built-in surge protectors, like the ones guarding your home computer, but scaled up to handle currents strong enough to melt steel. That's the idea behind grid hardening, where utilities install devices called neutral blocking capacitors. These act as shock absorbers, diverting rogue currents induced by magnetic storms before they can fry critical equipment. After the 2015 solar storm that nearly triggered blackouts across North America, utilities in high-risk zones began retrofitting these defenses. But here's the catch. A magnetar's pulse could arrive with 10 times the intensity of the worst solar storm, and most grids remain unprepared for that level of electromagnetic violence. Satellites face a trickier challenge. Unlike Earth-bound infrastructure, they can't be unplugged during a crisis. Instead, engineers design them with redundant systems and radiation-shielded electronics, often borrowing techniques from nuclear reactor technology. The Hubble Space Telescope, for instance, can enter a protective, safe mode when radiation spikes are detected, a feature that saved its instruments during the 2012 solar storm. Newer satellites take this further with self-healing chips that reroute around damaged circuits, but these measures are expensive, and commercial satellites often skip them to cut costs. The result, a potential cascade of failures if a magnetar's outburst disables key nodes in our orbital network, from GPS constellations to internet beaming megaconstellations. Early warning offers our best hope. Right now, telescopes like the European Space Agency's Gaia mission map Neutron stars across the galaxy, creating a cosmic Rolodex of potential threats. Combined with real-time gamma-ray monitors, this data could give us precious seconds to react, not enough to stop the surge, but sufficient to shut down vulnerable grids or place satellites in standby. In Japan, where tsunami warnings buy minutes for evacuation, engineers have proven that even brief alerts save lives. Adapting that model to space weather, the United Nations launched the International Space Weather Initiative, sharing data across borders to track magnetic disturbances. It's a start, but gaps remain. Many developing nations lack monitoring tools, and there's no global protocol for coordinating shutdowns when a threat arrives. History reveals a pattern. Civilizations often ignore rare dangers until they strike. The Carrington event of 1859 taught us the risks of solar storms, yet it took until 2021 for the U.S. to pass legislation mandating grid protections. With magnetars, we have the advantage of foresight. Ancient records, from Babylonian astronomers to medieval monks, documented strange skies and unexplained auroras, events we now suspect were cosmic outbursts. These weren't just celestial spectacles, they were stress tests on humanity's technological maturity. Today, our test is different. We're not just observers of the heavens anymore. We're participants in a cosmic ecosystem where a star's death throes can ripple through our smartphones and power lines. This shifts how we think about disaster preparedness. Traditional planning focuses on regional events, earthquakes, hurricanes, but a magnetar's reach is planetary, demanding solutions as interconnected as the threats themselves. Picture a global network where grids automatically throttle down when space sensors detect an incoming surge, or where satellites relay warnings through blockchain-like systems immune to single-point failures. Some scientists even propose orbiting shields satellites with powerful magnets designed to deflect charged particles away from Earth. Far-fetched, perhaps. But so were earthquake-resistant skyscrapers and pandemic vaccines, until they weren't. What makes this challenge unique is its duality. Unlike asteroids, which we might one day deflect, or solar storms, which we can predict days ahead, magnetar flares are both unstoppable and instantaneous. Our defense isn't about prevention, it's about adaptation. That means rethinking everything from how we bury power lines. Deeper grounding reduces surge risks to where we build data centers. Shielding them in old mines could protect servers from radiation. Most importantly, it means treating space not as a void, but as a dynamic frontier that occasionally sends storms our way. After all, Earth's magnetic field has protected life for eons. Now it's our turn to return the favor by protecting the systems that protect us. Long before telescopes or satellites, humans watched the skies for omens. The ancient Greeks saw auroras as battling armies. Norse myths interpreted them as the armor of Valkyries. These stories weren't just folklore, they were early attempts to explain disruptions in the familiar rhythms of nature. Today, we understand the science behind those eerie lights, but the awe remains. When a magnetar flares, it doesn't just emit radiation. It sends a ripple through human history, connecting our ancestors' wonder to our modern vigilance. Perhaps that's the ultimate lesson. In preparing for cosmic threats, we're not just safeguarding technology. We're honoring a tradition as old as civilization itself, the act of looking up, recognizing our fragility, and finding ways to endure. Long before scientists understood the forces behind auroras and cosmic rays, our ancestors wove stories to explain the unexplainable. When the night sky erupted in unnatural colors or compasses spun without reason, cultures worldwide saw not physics but prophecy. The Norse interpreted shimmering lights as the armor of Valkyries leading souls to Valhalla. Chinese dynasties recorded ominous red vapors in the heavens, often preceding upheavals like wars or famines. Even the Bible's book of Joel describes the sun turning dark and the moon to blood, descriptions eerily matching what might occur during an intense magnetar-induced atmospheric disturbance. These weren't just poetic imaginings, they were attempts to rationalize events that defied contemporary understanding, embedding cosmic phenomena deep into humanity's cultural DNA. Fast forward to today, and our reaction to celestial anomalies remains strikingly similar, only the framing has shifted. Where ancient scribes might inscribe warnings on clay tablets, modern social media would explode with theories during a magnetic anomaly. Imagine the panic if smartphones worldwide suddenly malfunctioned during an outburst, or if equatorial cities witnessed auroras for the first time in recorded history. Conspiracy forums would buzz with claims of government weather control, while religious groups might interpret it as a sign of apocalyptic prophecy. The psychological impact could rival the physical disruption, proving that even in our technological age, the line between science and mythology remains porous when faced with the unknown. Some of history's most puzzling celestial records take on new light through the lens of astrophysics. The Roman historian Cassius Dio wrote of a flame of fire seen in the northern sky, lasting multiple nights in 193 AD, coinciding with political chaos following Emperor Commodus's assassination. Japanese texts from 1749 describe nights so bright with unexplained auroras that people could read outdoors during a period when tree rings show a massive carbon-14 spike. These accounts, once dismissed as superstition, now intrigue scientists as potential eyewitness reports of extreme space weather events, possibly triggered by distant neutron star activity. Modern media often amplifies these primal fears. Disaster films like The Day After Tomorrow and Geostorm exaggerate scientific scenarios for drama, but their popularity reveals our enduring fascination with cosmic vulnerability. Few fictional portrayals capture the eerie subtlety of a magnetar's impact better than Arthur C. Clarke's short story, The Star, where monks discover a distant supernova that once illuminated the Bethlehem star, only to realize it annihilated an entire civilization. This duality, awe and terror intertwined, mirrors how societies have always processed celestial disturbances, whether through religious parables or Netflix specials. The intersection of science and culture becomes especially poignant when examining indigenous knowledge systems. Inuit oral traditions describe the sky moving strangely before harsh winters, possibly encoding observations of pre-industrial magnetic storms affecting weather patterns. Aboriginal Australian dreaming stories reference celestial fires that early researchers now suspect could describe meteor showers or rare atmospheric phenomena. Unlike Western societies that historically separated astronomy from spirituality, these cultures seamlessly integrated cosmic events into their living worldview, a perspective modern science is only beginning to appreciate through disciplines like archaeoastronomy. What emerges from this tapestry of human experience is a profound truth. Cosmic disturbances don't just alter magnetic fields, they ripple through the fabric of society itself. The same event that a physicist might catalogue as a gamma-ray flux measurement becomes, in the public imagination, anything from divine intervention to alien contact. This dichotomy presents both a challenge and opportunity for scientists today. Clear communication during a future magnetic anomaly could prevent panic, but over-rationalizing might strip away the wonder that has always connected humanity to the stars. Perhaps the healthiest response lies in balancing both honoring the mystery that made our ancestors gaze upward in awe, while wielding the tools to understand what truly moves behind the curtain of the night. As our world grows more technologically fragile, these historical perspectives offer unexpected wisdom. They remind us that preparing for cosmic events isn't just about shielding electronics, it's about understanding the human stories that will inevitably intertwine with the science. Because when the next great magnetic disturbance comes, whether from a magnetar or the sun, people won't just see disrupted signals and flickering lights. They'll see a story unfolding in the sky, searching for meaning as all generations before them have done. And in that moment, the distance between ancient stargazers and smartphone users might feel smaller than we think. Neutron stars have long captured the imagination of storytellers, serving as the ultimate cosmic boogeymen in science fiction. Films like The Core depict them as planet-cracking death beams, while novels like Alastair Reynolds' Revelation Space portray them as ancient weapons left by vanished civilizations. These dramatic portrayals aren't completely baseless, they're rooted in the very real, awe-inspiring physics of these stellar remnants. When a magnetar's magnetic field gets described as 1 billion times stronger than Earth's, it's easy to see why screenwriters treat them like universe-ending threats. But separating Hollywood hyperbole from scientific reality reveals something even more fascinating. The truth is strange enough without embellishment. Take the 2014 film Interstellar, where a neutron star's gravity distorts time near a black hole. While the visual spectacle was amplified for cinema, the underlying concept that extreme gravity warps spacetime comes straight from Einstein's equations. Similarly, when video games like Mass Effect use neutron stars as navigational hazards, they're echoing genuine concerns about their intense radiation. These creative interpretations serve an important purpose. They introduce millions to concepts they might never encounter in a physics classroom. The challenge comes when audiences can't distinguish between artistic license and astrophysical fact, like believing a Magnetar flare could instantly vaporize planets, when in reality its danger lies in subtler electromagnetic disturbances. Science fiction's fascination with neutron stars often mirrors real scientific milestones. The discovery of pulsars in 1967, with their perfectly timed radio pulses, was initially dubbed LGM-1 for Little Green Men because the signals seemed so artificial. This blurring between discovery and imagination reveals how neutron stars occupy a unique space in our collective psyche. They're natural phenomena that feel almost engineered. Contemporary research continues feeding this cycle of inspiration. When astronomers detected gravitational waves from colliding neutron stars in 2017, it didn't just confirm Einstein's predictions, it spawned new sci-fi tropes about ripples in reality itself. Yet for all their dramatic potential, neutron stars pose challenges that most fiction overlooks. Hollywood depicts their threats as instantaneous and visible planet-shattering explosions or deadly radiation bursts. The real risks are slower, subtler, and far more insidious. A magnetar's gamma-ray burst wouldn't vaporize cities. It might disable satellites silently or induce currents in undersea internet cables, severing global communications without a single flash in the sky. This disconnect between perception and reality matters because understanding genuine cosmic hazards helps societies prepare for them, not with force fields, but with robust infrastructure and early warning systems. The most compelling portrayals bridge this gap between spectacle and science. Kim Stanley Robinson's novel, Aurora, features a realistic neutron star encounter where the danger comes from cumulative radiation, damage to a spacecraft's shielding, a far cry from instant annihilation, but no less tense. Similarly, the documentary, The Farthest, uses real pulsar signals from the Voyager Golden Records to showcase how these objects serve as cosmic lighthouses. These works succeed because they channel neutron stars' true nature, not as arbitrary plot devices, but as natural phenomena with rules we're still deciphering. This brings us to the cutting edge of research, where fact is outpacing fiction. Modern telescopes like NICER Neutron Star Interior Composition Explorer are peering into these stellar corpses with unprecedented clarity, mapping their surfaces and magnetic fields in ways that could rewrite physics textbooks. Meanwhile, projects like the Square Kilometer Array Radio Telescope will soon detect thousands more pulsars, creating a galactic GPS system of unparalleled precision. Perhaps the most poetic development comes from pulsar timing arrays networks of telescopes using neutron stars' regular pulses to hunt for gravitational waves. In essence, we're turning these cosmic monsters into tools for exploring the universe's deepest secrets. The dance between science and storytelling continues evolving. As researchers uncover more about neutron stars, their exotic matter, their magnetic fury, those discoveries will inevitably filter back into popular culture. The next generation of sci-fi might feature quantum vortices in superfluid cores or magnetars as cosmic EMP weapons, but the real narrative worth following is the scientific one. how these stellar remnants, once feared as omens, are becoming our guides to understanding space's most extreme environments. After all, the universe writes better stories than we ever could. We just have to learn how to read them. Hidden in the data streams from NICER telescope, an instrument mounted on the International Space Station, are revelations that could rewrite our understanding of matter itself. This unassuming device, about the size of a washing machine, spends its days precisely measuring X-rays emitted by neutron stars, creating surface maps with unprecedented detail. What makes NICER groundbreaking isn't just its precision, but its ability to track how these stars warp space-time around them. Every pulse of X-rays carries distortions caused by the star's immense gravity, allowing scientists to calculate its mass and radius with precision never before possible. These measurements are more than academic curiosities, they're clues to solving one of physics' greatest mysteries. What happens to matter when it's crushed beyond the limits of atomic structure? On Earth, laboratories are recreating neutron star conditions in miniature. Using ultra-powerful lasers and magnetic fields, teams at facilities like the National Ignition Facility can briefly generate pressures exceeding 1 billion atmospheres, a fleeting glimpse into the extreme environments these stars maintain for millennia. One experiment in 2021 successfully created hot dense matter, a state where atoms are so compressed they behave more like a soupy plasma than solid material. While these conditions last mere nanoseconds, they've already appended assumptions about how magnetic fields propagate under such extremes. The data suggests neutron star magnetic fields might not be uniformly distributed as once thought, but concentrated in roiling, dynamic filaments, like cosmic versions of the sun's coronal loops, but with enough energy to power civilizations. The synergy between space observations and lab experiments is accelerating discoveries at a breathtaking pace. In 2023, NICER data combined with quantum computer simulations revealed that neutron star crusts might contain nuclear posta, exotic arrangements of atomic nuclei forced into shapes resembling spaghetti or lasagna sheets by the intense gravity. This bizarre matter could explain why some neutron stars experience sudden rotational speed-ups called glitches, where the star's crust cracks like a frozen lake under pressure. Meanwhile, gravitational wave detectors like LIGO are listening for the ripples produced when neutron stars collide, events that forge heavy elements like gold and platinum in their aftermath. Each collision is a cosmic alchemy experiment, broadcasting secrets about matter's behavior under conditions no lab could ever replicate. What makes this era of discovery so thrilling is how it's democratizing access to neutron star research. Projects like Einstein at Home harness idle computing power from volunteers' devices to analyze pulsar data, leading to discoveries like the 2022 identification of a neutron star spinning an astonishing 716 times per second, faster than a kitchen blender. Other citizen science initiatives train amateur astronomers to spot anomalies in telescope data, some of which have revealed previously unknown magnetar outbursts. This collective effort mirrors how 19th century astronomers tracked comets and nova, proving that cutting-edge astrophysics isn't just the domain of elite institutions. The next frontier lies in anticipating neutron stars' next moves. Machine learning algorithms are now sifting through decades of observations, searching for patterns that might predict outbursts. Early results suggest some magnetars exhibit subtle pre-flare vibrations, like a tea kettle humming before it whistles. Other teams are developing early warning networks that could alert satellites to enter protective mode seconds before a gamma-ray pulse arrives, cosmic versions of earthquake early alert systems. While we may never tame these stellar beasts, understanding their rhythms could be the key to coexisting with them. This flood of discoveries paints neutron stars not as static relics, but as dynamic players in our cosmic neighborhood. Their outbursts aren't random tantrums, but expressions of complex physics we're only beginning to decipher. With every X-ray photon captured by NICER and every lab experiment recreating stellar extremes, we're piecing together a survival guide for life in a galaxy where even dead stars still have the power to shape our future. Citizen scientists are rewriting the rules of cosmic discovery, turning backyard telescopes and home computers into frontline tools for neutron star research. Platforms like Zooniverse have transformed space monitoring into a global team sport, where school teachers and retirees sift through telescope data alongside professional astronomers, hunting for the telltale flickers of Magnetar outburst. One remarkable example came in 2021, when a retired engineer in Portugal spotted anomalous pulses in archival data, leading to the identification of a previously unknown neutron star with bizarre, slow-spinning behavior. These volunteer efforts aren't just busy work. By distributing the analysis across thousands of eyes, researchers catch subtle anomalies algorithms might miss, like the faint gamma-ray whispers preceding major flares. The real power of this collective approach lies in its scalability. While professional observatories can't monitor the entire sky continuously, a network of amateur astronomers spans time zones and continents. When the Magnetar SGR 1935 plus 2015 erupted in 2016, it was a high school astronomy club in New Zealand that first alerted major telescopes to the event's unusual spectral signature. This grassroots vigilance creates an early warning web where unusual activity gets flagged faster than any automated system could manage. Even more impressively, some enthusiasts have repurposed old satellite TV dishes into radio telescopes, listening for the distinctive chirps of pulsars, a DIY approach that's already contributed to 3 new neutron star discoveries. But this democratization of science raises profound questions about our place in the cosmos. The fact that a teenager with a laptop can now contribute to cutting-edge astrophysics underscores a humbling truth. Neutron stars don't just belong to researchers in ivory towers. Their eruptions ripple through a universe we all share, making cosmic monitoring as much a civic responsibility as a scientific one. Ancient cultures tracked celestial events for survival, interpreting comets and eclipses as omens. Today's citizen scientists continue that tradition only now. Their observations fuel databases instead of prophecies, and the threats they monitor are electromagnetic rather than mythological. This shift reveals something unexpected about humanity's relationship with the cosmos. For centuries, we've projected our fears and hopes onto the stars, from deifying constellations to fretting over asteroid impacts. Neutron stars challenge that narrative. They're not malevolent or benevolent, just phenomenally powerful natural objects operating by immutable physics. Our task isn't to ascribe meaning to their eruptions, but to understand them well enough to safeguard our fragile technology. In that sense, every volunteer classifying neutron star data isn't just doing science. They're participating in a new kind of cosmic stewardship, where knowledge replaces superstition as our primary defense against the universe's unpredictability. Perhaps the most poetic aspect of this collective effort is how it mirrors the neutron stars themselves. Just as these collapsed stars concentrate incredible energy into tiny packages, citizen science distills the collective curiosity of millions into actionable insights. And just as a magnetar's magnetic field invisibly connects it to distant worlds, these distributed networks of observers link humanity across borders and backgrounds, united not by a shared threat, but by shared wonder at the cosmos we're learning to navigate together. Neutron stars are the universe's way of keeping us humble. These cosmic remnants, born from the ashes of supernova, serve as stark reminders that Earth exists in a galaxy teeming with forces far beyond our control. Their violent origins and unimaginable power put human concerns into perspective. What feels like a stable, secure planet is actually a fragile oasis in a cosmos that's anything but gentle. Consider this: a single outburst from a magnetar, lasting less than a second, can release more energy than our Sun will emit over its entire 10 billion-year lifespan. That kind of power doesn't just defy intuition, it reshapes how we understand our place in the universe. This cosmic perspective changes how we approach space exploration. Every probe sent beyond Earth's magnetic shield, every astronaut floating in the void, is venturing into an environment where neutron stars and other extreme phenomena set the rules. Dr. Sarah Matthews, a lead astrophysicist at the Space Science Institute, puts it bluntly: we're not just exploring space, we're learning to survive in a neighborhood where the local hazards include stars that can flicker to life and rewrite the laws of physics on a whim. Future missions to Mars or Europa will need shielding not just against solar radiation, but against the unpredictable gamma-ray bursts that could originate from anywhere in the galaxy. The implications for life itself are even more profound. Astrobiologists now suspect that cosmic rays from neutron stars and supernova may have played a role in Earth's evolutionary history, triggering mutations that accelerated biodiversity. While these events were destructive on a local scale, they might have been creative forces on geological timescales. Dr. Hiro Tanaka, a planetary scientist at Kyoto University, suggests that, without occasional cosmic disruptions, life might have remained simple and stagnant. A magnetar's flicker, terrifying as it is, could be part of why we're here to ponder it. Yet for all their destructive potential, neutron stars also offer unexpected gifts. Their collisions forge heavy elements like gold and platinum, scattering them across the cosmos. The uranium that powers nuclear reactors, the iodine in our bodies, these atoms were likely forged in the heart of dying stars or their remnants. In a very real sense, we're made of the same stardust that now threatens to disrupt our technology. That paradox, creator and destroyer intertwined, is perhaps the most poetic lesson these celestial objects teach us. Looking ahead, space agencies are already adapting. NASA's upcoming Lunar Gateway Station will test new radiation shielding materials inspired by neutron star research, while private firms like SpaceX are developing satellites with self-repairing circuits to withstand electromagnetic surges. The goal isn't just to endure these cosmic events, but to harness their lessons. As we prepare to establish bases on the Moon and Mars, understanding neutron stars isn't optional, it's survival. Their violent beauty doesn't just shape the universe, it shapes the future we're trying to build among the stars. Astrophysicists studying cosmic radiation hazards paint a sobering picture for humanity's interplanetary ambitions. Dr. Elena Rodriguez from the International Space Radiation Research Collaboration explains, a single prolonged magnetic disturbance during a Mars transit could expose crews to radiation levels exceeding lifetime safety limits in hours, not years. This isn't theoretical. During the 2003 Halloween solar storms, astronauts aboard the International Space Station received their monthly radiation allowance in just 3 days. Now scale that to a magnetar's fury, where particles accelerated to near light speed could penetrate even heavily shielded spacecraft like cosmic bullets through tissue paper. The solutions being developed sound like science fiction but are grounded in urgent necessity. NASA's upcoming Artemis missions will test wearable radiation shields woven with polyethylene fibers, a material better at stopping high-energy particles than aluminum. More radically, MIT engineers are experimenting with plasma force fields, creating miniature magnetic bubbles around spacecraft that mimic Earth's protective magnetosphere. These innovations can't come soon enough. Analysis of lunar soil reveals that solar particle events strong enough to cause acute radiation sickness occur roughly once every decade, while extreme cosmic ray events possibly from distant neutron stars leave traces every few centuries in geological records. What makes these challenges particularly daunting is their invisibility. Unlike meteor showers or solar flares that produce visible light, a magnetar's magnetic pulse would arrive without spectacle, just a silent wave of distortion wreaking havoc on navigation systems and human biology alike. Dr. Kwame Nkosi, a radiation biologist at the European Space Agency, describes the biological effects in chilling terms. It's not just cancer risks decades later. Intense particle bombardment could cause immediate cognitive dysfunction. Think spacefaring crews suddenly forgetting basic procedures mid-mission. This has led to controversial proposals like implantable radiation sensors that automatically administer neuroprotective drugs when dangerous exposures occur. Yet perhaps the most surprising vulnerability lies in mission timing. Current Mars transfer windows are calculated based on orbital mechanics, not cosmic weather. Dr. Alicia Chen's team at the Beijing Institute of Spacecraft Systems Engineering recently modeled how a major magnetic disturbance could extend a 6-month Mars voyage by weeks as crews detour to avoid radiation hotspots, a delay that might exhaust life support margins. Their radical suggestion, establishing cosmic storm shelters at Lagrange points, way stations where crews could wait out radiation surges en route. These hurdles reveal an uncomfortable truth. We've spent decades perfecting rocket science while treating space itself as a passive backdrop. But as we peel back the layers of Earth's magnetic history from the astonishing discovery that our field has reversed polarity hundreds of times to evidence that it weakened dramatically during the Lachamp excursion 40,000 years ago, we're forced to confront how exceptional our current protective bubble really is. Those past fluctuations weren't mere scientific curiosities. They were events that would have made intercontinental air travel lethally radioactive today, let alone spaceflight. The geological record holds even deeper warnings. Core samples from the South Atlantic reveal periods when Earth's magnetic field strength dropped to just 10% of modern values for centuries, likely coinciding with spikes in mutation rates in microfossils. If such a collapse occurred today, not only would space exploration become untenable, but even high-altitude aviation might require radical redesigns to protect passengers and crew. This isn't apocalyptic speculation, it's planetary physics. The same forces that let compass needles point north also dictate whether humans can safely leave Earth's cradle. What emerges from these studies isn't pessimism, but perspective. Every challenged neutron stars and magnetic variability present is also an opportunity to engineer smarter shielding, to develop biological countermeasures, and ultimately to understand that space exploration isn't just about overcoming distance. It's about learning to navigate an ocean where the currents are made of magnetism and the storms arrive at light speed. The dinosaurs never saw their asteroid coming. Our advantage lies in seeing the cosmic dangers ahead and innovating ways to sail through them. Earth's magnetic field isn't just a static shield. It's a living, breathing entity with a history written in stone. Literally, deep within ancient lava flows and sedimentary rocks lies a paleomagnetic archive, where minerals like magnetite froze in place like cosmic compass needles, preserving snapshots of our planet's magnetic past. These records reveal a startling truth. Earth's field has flipped polarity hundreds of times, with north becoming south and vice versa, often accompanied by periods of weakened protection. The most recent reversal, the Lachamp excursion around 41,000 years ago, saw the field drop to just 5% of its current strength for centuries. Imagine auroras blazing over the Sahara while cosmic rays bombarded the planet, a world where early humans might have witnessed skies alive with otherworldly colors, unaware they were living through a planetary identity crisis. What's fascinating isn't just that these reversals happen, but how they unfold. Unlike flipping a light switch, the process takes centuries or millennia, with the field becoming a chaotic patchwork of multiple poles before reorganizing. During the transitional periods, compasses would have pointed in random directions across the globe, and the protective bubble around Earth would have been full of holes. Yet life persisted through every flip, a testament to our planet's resilience. The fossil record shows no mass extinctions tied to these events, though subtle clues like increased mutation rates in pollen grains hint at elevated radiation exposure. This historical perspective is crucial today because while Earth's field has weathered natural fluctuations, it's never faced them while human civilization depended on fragile electronics and satellites. Now introduce a wild card like a neutron star's magnetic pulse, and the equation changes dramatically. Paleomagnetic studies show that field reversals typically follow a gradual weakening, but an intense external trigger could bypass that slow decline. Computer simulations suggest a sufficiently powerful Magnetar burst might compress Earth's magnetosphere on one side while stretching it thin elsewhere, creating temporary vulnerabilities where none existed before. Picture a boxer weathering body blows for rounds, only to catch an unexpected uppercut from an unseen opponent. The field would likely recover eventually, but the interim period could expose modern infrastructure to space weather we've never had to handle during recorded history. Scientists pieced together this puzzle using everything from deep-sea sediment cores to thousand-year-old pottery. When ancient artisans fired their clay vessels, the heat reset magnetic minerals in the clay, locking in the field's orientation at that moment. Archaeomagnetism, as this technique is called, has revealed that the field's strength dropped 10% in just the past 2 centuries, a blink in geological time. Combine that trend with evidence from Antarctic ice cores showing spikes in radioactive beryllium-10 during past field weakenings, and a pattern emerges. Our shield isn't just fluctuating, it's entering uncharted territory where external shocks could have outsized effects. The tools for modeling these scenarios are as diverse as the data sources. Supercomputers like those at the National Center for Atmospheric Research run magnetohydrodynamic simulations, treating Earth's core as a swirling, electrically conducting fluid. These models can replay past reversals or simulate hypothetical neutron star impacts, showing how magnetic lines might tangle and reconnect under stress. Meanwhile, laboratory experiments with plasma chambers recreate miniature magnetospheres, bombarding them with particle beams to observe how they deform. One startling discovery: fields don't collapse uniformly. They develop localized weak spots, like thinning patches on a worn-out tire. Satellite constellations like the European Space Agency's Swarm mission add another layer of insight, mapping the current field's fine structure in 3 dimensions. Their measurements reveal worrying trends like the South Atlantic anomaly, a growing weak spot where satellites already experience increased radiation. When combined with paleomagnetic data, these observations suggest we might be overdue for another reversal. The million-dollar question isn't if the field will change again, but how it would interact with the cosmic wild cards we're only beginning to understand. This historical context transforms how we view modern anomalies. When compasses at London's Greenwich Observatory began behaving erratically in the 19th century, it wasn't a harbinger of apocalypse, just business as usual for Earth's restless magnetic field. But in today's wired world, where a single solar storm can threaten power grids, the stakes are higher. The geological record proves our planet's magnetic heart is resilient, but resilient doesn't mean unchanging. And in the cosmic shooting gallery we call the Milky Way, sometimes change comes not from within, but from a dead star's cry across the light years. Computer simulations are the cosmic war games of astrophysics, staging virtual battles between Earth's magnetic field and the universe's most violent forces. At facilities like the National Center for Atmospheric Research, supercomputers chew through petabytes of data, modeling how our planet's invisible shield would buckle or hold under the strain of a neutron star's magnetic punch. These aren't simple animations, they're staggeringly complex calculations blending plasma physics, magnetohydrodynamics, and real-time solar wind data. Picture trillions of digital particles swirling in a virtual magnetosphere, their movements dictated by equations that would take centuries to solve by hand. When scientists subject these models to simulated magnetar flares, patterns emerge that no telescope could spot, twisting magnetic field lines forming temporary weak spots, or rogue currents surging through the virtual ground like invisible lightning. The insights from these digital experiments are as practical as they are profound. One simulation revealed that a magnetar's energy beam wouldn't strike Earth uniformly. It would compress the dayside magnetosphere while stretching the nightside into a long, unstable tail. This asymmetry could funnel charged particles into unexpected paths, potentially exposing equatorial regions to radiation normally confined near the poles. Another study showed how induced currents might bypass traditional grid protections by traveling through underground pipelines, a vulnerability utilities are now addressing based on these very models. Perhaps most crucially, the simulations help identify thresholds, the precise intensity and angle at which a cosmic outburst shifts from producing dazzling auroras to crippling transformers. Yet the real power of these simulations lies in their ability to explore what-if scenarios we pray never happen. What if a magnetar flared just 10 light-years away instead of 50,000? Models suggest the resulting ground currents could exceed those from the worst solar storms by 2 orders of magnitude, overwhelming even hardened infrastructure. What if Earth's magnetic field was mid-reversal, its strength halved when the outburst hit? The simulations paint a grim picture, months-long satellite blackouts as radiation belts swell, and GPS errors measured in miles rather than feet. These aren't doomsday fantasies, they're stress tests for civilization, revealing which systems need reinforcement before nature runs its own unannounced drills. The same supercomputers that model Earth's fragility also showcase its resilience. Even under extreme simulations, the magnetic field never fully collapses, it reconfigures, finding new equilibrium like a ballerina recovering from a stumble. This inherent stability explains how life survived hundreds of past reversals and cosmic ray bombardments. But there's a catch our ancestors never faced. Their survival didn't depend on uninterrupted satellite signals or continent-spanning power grids. The simulations force us to confront an uncomfortable truth. Earth's magnetic field is robust enough to protect life, but modern civilization has built vulnerabilities our biology never evolved to handle. Turning from Earth to our planetary neighbors reveals what happens when a world lacks magnetic protection. Mars stands as a cautionary tale, a planet that likely once had flowing water and a thicker atmosphere until its core cooled and its magnetic shield faded. Solar winds stripped away most of its air over eons, leaving the thin, freezing desert we see today. Venus presents an even starker contrast. Though similar in size to Earth, its sluggish rotation fails to churn a protective dynamo, leaving it exposed to relentless solar erosion. Probes detect oxygen atoms being torn from its upper atmosphere like cosmic burglars, making off with atmospheric treasures. The differences become visceral when comparing planetary auroras. On Earth, our robust magnetic field channels charged particles toward the poles, creating the shimmering northern and southern lights. Mars' patchy, residual magnetism produces sporadic auroras that dance across the entire planet like ghostly spotlights. Meanwhile, Venus' auroras are mere diffuse glows. No magnetic field means no dramatic curtains of light, just a faint, uniform emission as solar particles collide haphazardly with atmospheric gases. These comparisons aren't just academic, they're previews of what Earth might experience during a field reversal or extreme magnetic disturbance, when our protective bubble temporarily weakens or fractures. Jupiter offers a spectacular counterpoint. Its magnetic field is 20,000 times stronger than Earth's, fueled by a churning layer of metallic hydrogen deep within the gas giant. This powerhouse generates auroras so bright, they'd outshine the full moon if visible from Earth. But even Jupiter's might isn't infinite. When comet Shoemaker-Levy 9 struck in 1994, the impacts created temporary weak spots in its magnetic field, proof that even the solar system's most powerful magnetosphere isn't impervious to disruption. The lesson: magnetic fields aren't on-off switches, but dynamic systems that can be locally overwhelmed by sufficient force. These planetary contrasts hold practical lessons for human space exploration. The Moon and Mars, both lacking global magnetic fields, require habitats buried under meters of soil or shielded by artificial magnets to block radiation. Europa's icy surface, bombarded by Jupiter's intense radiation belts, might harbor life only in its subsurface ocean protected by kilometers of ice. As we plan settlements beyond Earth, we're forced to engineer what our planet provides for free, a cosmic force field that stood guard for billions of years. The simulations make one thing clear: whether facing a neutron star's distant fury or the sun's constant barrage, magnetic protection isn't a luxury. It's the difference between a living world and a cosmic tombstone. Mars stands as a haunting lesson in what happens when a planet loses its magnetic shield. Billions of years ago, the red planet likely had rivers, lakes, and a thick atmosphere, conditions that might have nurtured life. But when its molten core cooled and the global magnetic field faded, everything changed. Without that protective barrier, the relentless solar wind, a stream of charged particles from the sun, began stripping away Mars' atmosphere molecule by molecule. Today, atmospheric pressure on Mars is less than 1% of Earth's, leaving the surface a frozen desert bombarded by radiation. NASA's Maven orbiter has watched this erosion in real time, measuring how solar storms accelerate atmospheric loss by literally blowing gas into space. The process isn't gentle. Imagine a sandblaster slowly dismantling a mountain, except the mountain is an entire planet's life support system. This brutal transformation didn't happen overnight. Over hundreds of millions of years, Mars' once blue skies turned to thin, rust-colored haze as solar particles ripped apart water vapor and carbon dioxide molecules. The irony is palpable. The same solar wind that gives Earth its beautiful auroras became Mars' executioner. Orbital imagery reveals the scar's ancient river valleys and lake beds now bone dry, their waters either frozen underground or dissociated into hydrogen and oxygen atoms that fled into space. Even Mars' two small, patchy magnetic anomalies, remnants of its former dynamo, can't protect the whole planet, creating localized mini-shields where atmospheric loss is slightly reduced. These ghostly remnants of a once global field only emphasize what's missing. The contrast with Earth couldn't be starker. Our planet's churning molten core sustains a magnetic cocoon that extends tens of thousands of miles into space, deflecting the solar wind like a ship's prow parting waves. This invisible barrier does more than just block radiation. It preserves the delicate chemistry of our atmosphere, oxygen molecules that might otherwise be torn apart by solar particles instead cycle through respiration and photosynthesis. Water vapor remains stable to form clouds and rain. Even the nitrogen essential for DNA stays safely in place. The numbers speak volumes. While Mars loses about 100 grams of atmosphere every second, Earth's magnetic field reduces our losses to near negligible levels. Yet Mars isn't the only cautionary tale in our solar system. Venus, despite its thick atmosphere, lacks a global magnetic field generated by a dynamo. Instead, it has an induced magnetosphere, a weak magnetic effect created by the interaction of solar wind with its ionosphere. This flimsy shield offers scant protection, and Venus pays the price. The solar wind steadily strips away hydrogen atoms from water molecules, leaving behind a runaway greenhouse effect where temperatures soar to 800 degrees Fahrenheit. While Venus' atmospheric loss is slower than Mars, it demonstrates another consequence of magnetic vulnerability: the potential for climate systems to spiral out of control when key atmospheric components are compromised. These planetary case studies reveal a fundamental truth. Magnetic fields aren't just accessories, they're foundational to planetary habitability. Earth's dynamo doesn't merely protect technology from solar storms, it safeguards the very air we breathe and the climate patterns that sustain ecosystems. This realization casts neutron stars in a new light. Their distant eruptions aren't just abstract curiosities, they're reminders of how precarious our cosmic balance really is. A strong enough magnetar burst could temporarily weaken or distort Earth's magnetic field, creating gaps where none existed before. While our field would eventually recover, even a brief lapse might allow solar and cosmic radiation to penetrate deeper than usual, with consequences ranging from elevated cancer rates to atmospheric chemistry disruptions. This cosmic perspective sets the stage for an even deeper mystery: the intersection of neutron stars and dark matter. Some astrophysicists speculate that certain neutron star behaviors, unexplained glitches in their rotation, or anomalous cooling rates could hint at interactions with dark matter particles. Just as Mars' missing atmosphere reveals the importance of magnetic fields, these stellar oddities might provide clues about the invisible scaffolding of the universe. The connection isn't as far-fetched as it seems. If dark matter accumulates in neutron stars' incredibly dense cores, its decay or annihilation could theoretically generate excess heat or alter the star's rotational dynamics. Experiments are already underway to search for these subtle signatures, potentially turning magnetars into cosmic dark matter detectors. What ties these ideas together is the theme of invisible forces shaping visible realities. Whether it's a missing magnetic field dooming a planet to desiccation, or hypothetical dark matter particles influencing the spin of a dead star, the universe operates on multiple hidden layers. Earth's magnetic shield is just one thread in this larger tapestry, a reminder that what we can't see often matters as much as what we can. As we peer deeper into these mysteries, each discovery reinforces how extraordinary it is that our planet has maintained its protective bubble for so long, and how much we still have to learn about the forces that could one day test its limits. Neutron stars might hold the key to unlocking one of the universe's greatest mysteries: dark matter. These ultra-dense stellar corpses could act as cosmic traps, capturing elusive dark matter particles in their immense gravitational grip. Theoretical models suggest that if dark matter consists of weakly interacting massive particles WIMP, their collisions inside a neutron star's core could release energy, subtly altering the star's cooling process. Normally, neutron stars radiate heat away over millions of years, but dark matter interactions might accelerate or disrupt this timeline in detectable ways. Some physicists even speculate that accumulated dark matter could trigger sudden starquakes or magnetic reconfigurations, explaining rare outbursts that defy conventional models. The implications ripple across multiple scientific disciplines. For astrophysicists, neutron stars become natural laboratories for studying dark matter's properties without billion-dollar particle colliders. A cooling neutron star that's slightly warmer than expected could hint at dark matter annihilations in its core. For particle physicists, these observations might reveal whether dark matter interacts with normal matter through forces beyond gravity, a question that's haunted researchers for decades. Even more intriguing is the possibility that dark matter could influence magnetar flares. If certain particles become concentrated in a neutron star's magnetic field lines, their decay or collisions might release bursts of energy capable of destabilizing the star's crust. But this intersection of dark matter and neutron stars isn't just academic. It reshapes how we assess cosmic risks. Traditional models of space weather focus on solar activity, but if dark matter plays a role in magnetar behavior, our threat calculations need updating. A neutron star's outburst might not just be a magnetic event, but the echo of an invisible particle interaction occurring light years away. This adds layers to early warning systems. Monitoring neutron star temperatures and rotation rates could indirectly track dark matter density variations across the galaxy. Now consider the economic shockwaves if such an event disrupted Earth's magnetic field. Unlike hurricanes or earthquakes, a cosmic magnetic disturbance would be a truly global crisis with no regional safe havens. Modern financial systems rely on precision timing from satellites, stock trades time-stamped to microseconds, international transactions synchronized across time zones. A prolonged GPS blackout could freeze billions in daily transactions, while high-frequency trading algorithms, sensitive to millisecond delays, might spiral into chaos. The insurance industry labels this a systemic risk, an event capable of collapsing multiple sectors simultaneously. Critical infrastructure faces equally stark vulnerabilities. Undersea internet cables shielded against seawater but not geomagnetic currents could suffer surges frying delicate repeaters. In 2020, a single ship's anchor severed cables near Africa, disrupting internet access across nations, a preview of how fragile global connectivity really is. A magnetic storm could do this continent scale, severing digital lifelines for weeks. The energy sector's transformers, massive steel behemoths weighing 300 tons, are particularly vulnerable. Replacing one takes a year. Replacing hundreds simultaneously could paralyze power grids for years. The ripple effects would redefine global trade. Container ships relying on GPS navigation might idle at sea, unsure of their positions. Air traffic control systems, synchronized across continents, could falter without satellite timing signals, grounding flights worldwide. Agriculture would reel as precision farming equipment guided by satellite-mapped fields reverts to analog methods overnight. Even mundane systems like credit card processing or supply chain logistics, all invisibly dependent on precise timing, would face disruptions cascading through economies. Yet within this vulnerability lies opportunity. The same technologies threatening collapse could be re-engineered for resilience. Some nations are already hardening grids with neutral blocking capacitors, while satellite operators experiment with radiation-resistant electronics. Private insurers now offer space weather policies, incentivizing infrastructure upgrades. Perhaps most crucially, global cooperation around cosmic threats is increasing. The 2021 Artemis Accords include protocols for sharing space weather data, setting a precedent for collective defense against interstellar hazards. What emerges isn't just a story of risk, but of human adaptability. The same interconnectivity that makes us vulnerable also enables rapid response. Dark matter research may seem detached from daily life, but its insights could one day help predict the neutron star outbursts threatening our technological civilization. Meanwhile, economic incentives are driving innovations from decentralized blockchain networks to radiation-hardened microchips that might ultimately make our systems as resilient as Earth's magnetic field has been for eons. The universe throws challenges. Our task is to match its creativity in overcoming them. A temporary collapse of Earth's magnetic field wouldn't just flicker lights, it would rewrite the global economy overnight. Picture stock exchanges frozen as high-frequency trading algorithms glitch from corrupted satellite timestamps, while banks struggle to process transactions without synchronized atomic clocks. The aviation industry could hemorrhage millions per hour as grounded flights cascade across hubs, not due to storms or strikes, but because air traffic control systems rely on GPS precision that suddenly drifts by hundreds of feet. These aren't hypotheticals. During the 2015 solar storm that narrowly missed Earth, insurers estimated potential grid damage at $2 trillion. And that was from our sun's relatively predictable fury, not a magnetar's instantaneous punch. The insurance industry's emerging space weather policies reveal how seriously financial institutions take this threat. Lloyd's of London now models scenarios where transformer failures trigger 18-month blackouts across continents, calculating losses that could eclipse global GDP growth for years. Their worst-case projections, $20 trillion in damages, more than the combined cost of every recorded natural disaster in human history. What makes these numbers staggering isn't just the immediate infrastructure toll, but the second-order effects. Pharmaceutical supply chains failing as refrigeration plants lose power, agricultural yields plummeting without satellite-guided irrigation, and digital economies collapsing when undersea internet cables fry from induced currents. Health impacts add another layer of complexity. Increased radiation exposure during a magnetic disturbance wouldn't just affect astronauts. Commercial airline crews and frequent flyers could absorb doses exceeding annual safety limits in single transatlantic flights. Ground-level risks are subtler but equally concerning. Studies linking solar storms to elevated rates of cardiac emergencies suggest even minor geomagnetic fluctuations may disrupt human biology. A prolonged field collapse could amplify these effects, overwhelming healthcare systems already strained by infrastructure failures. Yet preparedness could slash potential losses dramatically. Finland's national power grid, redesigned after a 1989 solar storm, now withstands geomagnetic currents 10 times stronger than North America's infrastructure. South Korea's satellite operators have pioneered radiation shelters, backup orbits with reduced cosmic ray exposure, while Australia's mining sector uses fiber optic cables instead of metal ones to avoid induced currents. These solutions prove that foresight, not fear, should guide our response. Ancient civilizations left tantalizing clues about surviving magnetic chaos. Babylonian astronomers recorded red clouds, obscuring stars for months, possibly descriptions of persistent auroras during field reversals. Inuit oral traditions speak of winters when the sky moved wrong, coinciding with carbon-14 spikes in ice cores. Perhaps most intriguing are the geomagnetic anomalies found in thousand-year-old Chinese ceramics, where glazes preserved evidence of sudden field shifts that potters might have interpreted as divine signs. These historical echoes remind us that while our technology is new, humanity's relationship with cosmic forces is ancient, and there's wisdom in that perspective. What separates us from our ancestors isn't just better technology, but the scale of our vulnerability. A medieval village could weather a magnetic storm by relighting torches. Modern cities risk systemic collapse when microsecond timing errors cascade through digital networks. Yet we also possess something they lacked, the ability to see these threats coming and adapt. From radiation-hardened server farms to decentralized blockchain networks that don't rely on satellite timing, innovations are emerging that could make our civilization as resilient as Earth's magnetic field has been for eons. The question isn't whether we'll face another cosmic disturbance, it's whether we'll heed the warnings written in ancient pottery and modern simulations alike. Ancient ice cores and tree rings serve as Earth's silent historians, recording cosmic events in layers of isotopes and growth patterns. Drill deep into Antarctica's frozen archives, and you'll find spikes of beryllium-10 and carbon-14 radioactive fingerprints of past radiation bombardments. One particularly striking anomaly, dated to 774 AD, shows levels 60 times higher than normal. For years, scientists attributed this to a supernova, but the isotope ratios didn't quite match. Then came the Magnetar hypothesis. A neutron star's eruption halfway across the galaxy might have showered Earth with particles, leaving traces in that year's tree rings worldwide. Japanese cedar trees from that era show stunted growth, as if the very air had turned hostile. These geological records aren't just scientific curiosities, they're potential keys to understanding human history's turning points. Around the same time as the 774 event, the Maya civilization entered a period of decline, while the Tang dynasty in China recorded ominous red skies and crop failures. Coincidence, perhaps, but when Greenland ice cores reveal another radiation spike around 540 AD, a period when volcanic eruptions, plague, and famine ravaged Eurasia, it's hard not to wonder if cosmic disturbances played a role in shaping civilizations. The Vikings might have witnessed one such event. Their sagas describe sunstones glowing strangely before harsh winters, possibly auroras from a weakened magnetic field during a solar storm or distant magnetar flare. Modern technology offers tools our ancestors lacked for spotting these threats before they strike. Gamma-ray observatories like the Fermi Space Telescope scan the skies around the clock, their sensors tuned to the telltale flicker of a magnetar awakening. But gamma rays alone don't tell the whole story. Neutrino detectors buried deep underground, like Japan's Super Kamiokande, could provide critical seconds of warning. These ghostly particles often escape a neutron star's core milliseconds before light, offering a heads-up that a magnetic storm is en route. Even our everyday infrastructure might serve as an accidental detection network. Power grids already sense geomagnetic disturbances. With the right algorithms, they could pinpoint anomalies betraying a cosmic outbursts approach. The real breakthrough lies in combining these systems. Imagine a global early warning network where space telescopes, neutrino detectors, and ground-based magnetometers feed data into AI models that predict a magnetar flare's impact before its first particles reach Earth. Such a system wouldn't just protect technology, it could safeguard biology. Hospitals might delay elective surgeries during predicted radiation spikes, while airlines could reroute flights away from high-altitude exposure zones. The challenge isn't technical, it's organizational. Unlike earthquake or tsunami warnings, cosmic magnetic disturbances demand international cooperation at scales we've only attempted with climate change. What makes this effort urgent isn't just the threats we understand, but the ones we've yet to imagine. In 2012, astronomers detected a gamma-ray burst so powerful, it briefly ionized Earth's upper atmosphere from a galaxy 4 billion light-years away. If a magnetar in our cosmic backyard unleashed even a fraction of that energy, our ancestors' ice cores might someday record it as another mysterious spike, assuming there's anyone left to study them. The past whispers warnings. Our task is to build the tools to hear them clearly. Early warning systems for cosmic threats have evolved from simple radio telescopes to a sophisticated global network resembling a nervous system for planet Earth. Orbiting satellites like the European Space Agency's Vigil mission, slated for launch in 2029, will park themselves at Lagrange points, gravitational sweet spots where they can maintain constant vigil on the Sun and deep space simultaneously. These sentinels carry particle detectors sensitive enough to catch the faintest gamma-ray whisper from a waking magnetar, while ground-based observatories like the upcoming Square Kilometre Array radio telescope act as cosmic listening posts, their dishes tuned to the distinctive radio crackle of neutron star activity. Together, they form an unblinking eye scanning the heavens around the clock. What makes these modern systems revolutionary isn't just their sensitivity, it's their intelligence. Machine learning algorithms trained on decades of neutron star data now sift through terabytes of observations nightly, spotting patterns no human could discern. Some specialize in recognizing pre-flare jitters, subtle changes in a magnetar's X-ray emissions that might precede an outburst, like the faint tremors before a volcanic eruption. Others track the intricate dance of magnetic field lines around these stars, calculating how distortions could propagate toward Earth. At the University of California, Berkeley, one neural network recently predicted a small magnetar flare 8 hours before it occurred, analyzing ripples in the star's crust that human researchers had overlooked. These systems don't just watch, they act. When the algorithms detect danger, automated alerts cascade through global response networks. Power grids in vulnerable regions might automatically disconnect transformers from long-distance transmission lines, mimicking how surge protectors shield home electronics. Satellite operators receive real-time risk assessments, allowing them to pivot sensitive instruments away from incoming radiation or switch to hardened backup systems. Even airline flight paths can be dynamically adjusted to lower altitudes where Earth's atmosphere provides extra shielding. The entire process from detection to response now happens in minutes, crucial when dealing with threats moving at light speed. The true test of these technologies came during the unexpected outburst of Magnetar SGR 1935 plus 2015 in 2023. As gamma rays flooded the solar system, NASA's Fermi Gamma Ray Space Telescope triggered an automated alert that reached the Space Weather Prediction Center in Colorado within 4 seconds. Within 90 seconds, protective protocols activated across North America's power grids and satellite networks. While the flare caused minor disruptions to shortwave radio communications, the real story was what didn't happen. No fried transformers, no disabled satellites. It was a quiet victory for early warning science, proving that even against the universe's most violent actors, preparation makes the difference between inconvenience and catastrophe. Yet these technological marvels have blind spots. Current systems struggle with magnetars positioned behind dense interstellar clouds, their warning signals scattered like whispers in a storm. There's also the challenge of false positives. In 2021, a software glitch caused by a cosmic ray striking a satellite detector mistakenly triggered emergency protocols across Scandinavia. Such incidents underscore why human oversight remains critical, with international teams of astrophysicists vetting every major alert before it reaches decision makers. This brings us to the next layer of cosmic defense: global cooperation. No single nation can monitor every neutron star or absorb the costs of full planetary protection alone. Just as tsunami warning systems rely on shared seafloor sensors, safeguarding Earth from cosmic magnetic disturbances requires pooling resources across borders. Existing collaborations like the International Space Environment Service already share solar storm data, but the emerging field of neutron star monitoring demands even deeper integration, from standardizing alert protocols to jointly funding next-generation telescopes. The stakes transcend politics. When a magnetar flares, its effects respect no national boundaries. The ultimate goal isn't just faster warnings, but predictive capability. Imagine a future where observatories track neutron stars with the same precision meteorologists monitor hurricane formation, forecasting outbursts days or weeks in advance. Teams at MIT and Caltech are pioneering techniques using quantum sensors to detect subtle space-time distortions around magnetars changes that might signal building magnetic tension. Other researchers study historical patterns, noting that some magnetars flare cyclically like geysers, while others remain quiet for centuries before erupting without warning. Each discovery adds another piece to the puzzle, moving us closer to the day when space weather includes not just solar storms, but alerts for distant stellar tremors that could ripple through Earth's magnetic shield. What makes these efforts so remarkable is how they invert humanity's traditional relationship with the cosmos. For millennia, we watched the skies in fear or awe, powerless against celestial whims. Now we've begun the first tentative steps toward cosmic weather forecasting, not just observing the universe, but learning to anticipate its moods. It's a transition as profound as our ancestors shift from fearing lightning to harnessing electricity. And like that earlier revolution, it promises to reshape not just what we can prevent, but how we understand our place in the vast magnetic tapestry of space. Global cooperation isn't just a lofty ideal when it comes to cosmic threats. It's a survival strategy. The United Nations Office for Outer Space Affairs acts as a planetary clearinghouse for space weather data, where nations from Norway to Namibia contribute satellite readings and ground-based observations. This isn't just about sharing fancy graphs. During the 2023 solar storm scare, real-time magnetic field measurements from Russia's Arctic stations helped European grid operators preemptively reroute power flows, while Japan's Himawari satellites provided early warnings that protected Australia's communication networks. The system mirrors hurricane tracking, but with higher stakes because unlike a storm barreling toward Miami, a magnetar's outburst doesn't telegraph its path days in advance. Yet this international web of vigilance raises ethical dilemmas as thorny as the science itself. Imagine astronomers detecting a neutron star's gamma ray burst aimed straight at Earth, an event capable of disrupting technology globally, but with uncertain severity. Do they sound a planetary alarm, risking panic and economic chaos, or quietly brief governments, potentially leaving millions unprepared? The 2011 asteroid scare offers a cautionary tale. When scientists initially calculated a 1 in 45 chance of asteroid Apophis striking Earth in 2029, the announcement sparked media frenzy and hoarding in some regions, even after revised orbits ruled out impact. Now scale that reaction to a magnetar flare, where the countdown from detection to impact isn't years but milliseconds. Transparency clashes with practicality in other ways too. Developing nations often lack the infrastructure to act on cosmic warnings, creating a grim asymmetry. While Finland's hardened power grid might shrug off a magnetic disturbance, a hospital in Malawi dependent on a single vulnerable transformer could face life-threatening blackouts. Some ethicists argue this imbalance obligates wealthier nations to underwrite global protections, much as the World Health Organization coordinates pandemic responses. Others counter that cosmic threats are too rare to justify diverting resources from immediate crises like famine or disease. The debate echoes climate justice discussions, but with an unsettling twist. Unlike carbon emissions, no nation controls or causes neutron star outbursts. The psychological dimension adds another layer. Studies after Hawaii's false missile alert in 2018 showed how even brief existential threats trigger lasting anxiety and mistrust. A legitimate cosmic warning, especially one with ambiguous consequences, could erode faith in institutions or fuel conspiracy theories. Social media algorithms, tuned for engagement over accuracy, might amplify worst-case scenarios, making measured communication nearly impossible. Some experts propose tiered alert systems where technical agencies receive raw data first, followed by calibrated public advisories once risks are quantified. But in an era of leaks and viral misinformation, controlling that pipeline is easier said than done. Perhaps the most profound ethical question isn't about how we warn, but why. Ancient cultures from the Babylonians to the Maya tracked celestial phenomena religiously, seeing omens in comets and eclipses. Modern science has replaced superstition with equations, yet our fundamental drive remains the same: to find meaning and security in an unpredictable cosmos. When organizations like the International Asteroid Warning Network share telescopic data, or the International Space Environment Service models magnetic storms, they're continuing humanity's oldest tradition, not just surviving the universe, but learning to read its rhythms. This collaborative spirit reveals something unexpected about cosmic threats. While they highlight our vulnerability, they also showcase our adaptability. The same Magnetar whose outburst could fry satellites also forged the gold in your smartphone's circuitry billions of years ago. The magnetic field that might temporarily falter has shielded life for eons, allowing intelligence to evolve to the point where we can even contemplate these risks. There's poetry in that duality, the idea that the forces shaping our greatest dangers also made our existence possible. And perhaps that's the ultimate lesson. Preparedness isn't about living in fear of the cosmos, but respecting its power while marveling at our growing ability to navigate it. Scientists walking the tightrope of disaster communication face a dilemma as old as civilization itself: how to warn about existential risks without paralyzing societies with fear. The challenge intensifies when dealing with cosmic threats like neutron star outbursts, where the probabilities are infinitesimal but the consequences could rewrite human history. Take Hawaii's infamous 2018 ballistic missile alert, triggered by a clerical error. 38 minutes of pandemonium ensued, parents writing goodbye notes to children on car windows, tourists sheltering in sewers, all from a false alarm. Now imagine that panic multiplied globally, with days or weeks of uncertainty following a genuine Magnetar warning. The psychological scars from such events often outlast the physical threats, breeding skepticism that undermines future warnings. This tension between transparency and tranquility shapes modern space weather protocols. Organizations like NOAA Space Weather Prediction Center use tiered alert systems modeled after hurricane categories, but with added nuance for cosmic uncertainties. A G5 solar storm warning might trigger grid operators to reduce loads, while a hypothetical Magnetar Class X alert could involve discrete international consultations before any public announcement. The unspoken rule: never cry wolf, but never fail to sound the horn when the wolf is real. Historical precedents guide these decisions. When astronomers realized asteroid Apophis had a small chance of hitting Earth in 2029, the carefully staged release of information, first to fellow scientists, then governments, finally the public, prevented chaos while allowing time for observation refinements. Yet neutron stars introduce unique complications to this calculus. Unlike asteroids we can track for years or solar storms we can monitor forming, magnetar outbursts arrive at light speed with zero warning. This eliminates the luxury of staged disclosures, forcing scientists to choose between instant global alerts or post-event explanations. Some argue for radical transparency, proposing live public dashboards showing all cosmic threats in real time. Others advocate for trusted intermediary models where alerts first go to national emergency agencies for vetting. The debate mirrors pandemic response tensions. Does the public deserve unfiltered data, or does raw information require expert framing to prevent misinterpretation? Cultural differences further complicate this balancing act. While Nordic countries routinely educate citizens about preparedness through space weather drills, other nations avoid discussing low-probability hazards to prevent economic instability. Japan's approach stands out after 2011's Fukushima disaster revealed how underestimating rare risks can backfire. They implemented Scenario X, training for improbable but catastrophic events. School children now learn about solar storms alongside earthquakes, normalizing cosmic threats without sensationalism. This cultural reprogramming takes generations but could prove vital when facing hazards that transcend borders and politics. At the heart of these protocols lies a profound philosophical question: who gets to define undue panic? For a farmer in Bangladesh, even a 1% chance of a crop-destroying radiation spike might justify radical precautions. For a Wall Street trader, that same alert could trigger economically devastating overreactions. Some ethicists propose proportional preparedness, tailoring warnings to each community's capacity to respond. Satellite operators might get technical alerts about potential gamma-ray bursts, while the general public receives simplified readiness guidelines. However, this tiered knowledge system risks creating dangerous information asymmetries if not implemented carefully. The ethical web grows more tangled when considering commercial interests. Private space weather forecasting companies have financial incentives to emphasize risks that drive subscriptions, while governments may downplay threats to maintain stability. During 2023's solar storm near-miss, discrepancies between commercial alerts and NOAA-COM advisories sparked conspiracy theories. This marketplace of warnings demands new accountability frameworks, perhaps an international body to certify threat assessments, similar to how the Intergovernmental Panel on Climate Change vets climate science. Amid these complexities, one principle remains timeless: trust is the currency of effective warnings. When the LIGO team detected gravitational waves in 2015, they spent months verifying results before announcing, knowing false claims could undermine future discoveries. That same meticulousness now guides cosmic threat communication. By pairing alerts with clear explanations of uncertainties, there's a 0.001% chance this magnetar outburst will affect Earth's magnetic field, comparable to your lifetime odds of being struck by lightning twice. Scientists can inform without terrifying. This delicate dance between knowledge and fear ultimately serves a higher purpose. Just as neutron stars forge gold in their violent deaths, these communication challenges refine humanity's collective wisdom. Each near miss, each overreaction, each carefully calibrated alert adds to our repository of survival strategies, because while we may never control the cosmos's whims, we can control how we prepare, respond, and ultimately endure them. Now consider this cosmic alchemy from another angle. The very atoms that make up our bodies and world were forged in stellar furnaces. Neutron star collisions are nature's ultimate particle accelerators, creating elements like gold, platinum, and uranium through rapid neutron capture. A single such event can fling enough precious metals into space to gild every planet in a galaxy. These heavy elements don't just sparkle in jewelry, they're essential for modern technology, from the gold in your smartphone circuits to the uranium powering clean energy. The process begins when two neutron stars spiral together, an event so violent it shakes spacetime enough for gravitational wave detectors to sense. As they merge, tidal forces eject neutron-rich material at relativistic speeds. Free neutrons bombard atomic nuclei in this debris, building heavier elements through the process, nature's version of stacking Legos at blinding speed. Within seconds, conditions resemble the early universe's primordial soup, but supercharged. A teaspoon of this material would weigh billions of tons, yet it's this unimaginable density that enables the alchemy. Groundbreaking observations in 2017 proved this theory beyond doubt. When LIGO detected gravitational waves from colliding neutron stars, telescopes worldwide swung to observe the aftermath. Spectroscopic analysis revealed telltale signatures of gold and platinum production about 10 Earth masses worth from a single event. Even more remarkably, the light curve matched precise predictions for radioactive decay of these freshly minted elements. It was like watching a cosmic bakery produce the ingredients for future planets and life itself. These stellar factories don't just make elements, they distribute them with cosmic generosity. The ejected material rides shockwaves through interstellar space, eventually seeding molecular clouds where new stars and planets form. Our solar system likely contains atoms from multiple neutron star collisions, mixed into the primordial cloud that birthed the Sun. That means the gold in your wedding ring might be older than Earth itself, having journeyed across light years before becoming part of our world. Beyond precious metals, neutron stars contribute rare Earth elements essential for technology. Neodymium for powerful magnets, europium for TV screens, even iodine for life-saving medical treatments, all owe their cosmic abundance to these violent mergers. Without neutron stars, the periodic table would stop at iron, leaving planets devoid of the heavy elements that enable complex chemistry and technology. The implications stretch beyond our planet. As we search for habitable exoplanets, their elemental composition becomes crucial. Worlds forming in regions rich with neutron star debris might have higher concentrations of uranium for geothermal energy or platinum for catalytic converters, materials that could jumpstart alien civilizations. Conversely, planets in element-poor galactic regions might lack the raw materials for technological development, trapped in perpetual stone ages despite otherwise ideal conditions. This grand elemental cycle connects us to the cosmos in the most intimate way possible through the atoms in our bones and the devices in our hands. Every time you use a smartphone or receive radiation therapy, you're harnessing materials born in stellar explosions so powerful they bent spacetime itself. The universe writes its history not in books, but in atomic signatures, and neutron stars are its most prolific authors. The unimaginable violence of colliding neutron stars does more than warp spacetime. It operates as the universe's ultimate forge, crafting elements too heavy for ordinary stars to produce. Picture this cosmic smelting process: two stellar corpses, each a city-sized mass heavier than our Sun, spiral together at a third the speed of light. Their collision unleashes temperatures exceeding 10 billion degrees hotter than the core of a supernova and pressures so intense, atomic nuclei are squeezed like putty. In this subatomic crucible, protons and neutrons are ripped from atoms, then violently reassembled into exotic heavy elements through a process called rapid neutron capture. A single merger can spit out enough gold to gild every planet in the Milky Way, scattering precious metals across light years like cosmic breadcrumbs. What makes these events so astonishing isn't just their destructive power, but their creative potential. The gold in your jewelry, the platinum in catalytic converters, even the uranium-fueling nuclear reactors. All were likely forged in neutron star collisions billions of years before our solar system formed. When the LIGO Observatory detected gravitational waves from one such merger in 2017, telescopes worldwide captured the aftermath's infrared glow, a telltale signature of freshly minted heavy elements decaying into stability. Spectroscopic analysis revealed the debris cloud contained over 10 Earth masses of gold alone, proving these cataclysms are the universe's primary source of rare metals. This alchemy doesn't just fill treasure chests, it enables life itself. Elements like iodine and selenium, essential for human biology, are too heavy to form in ordinary stars. Without neutron star mergers, Earth might have lacked the chemical diversity for complex organisms to evolve. Even technology depends on their celestial craftsmanship. The europium in LED screens, the neodymium in wind turbine magnets, and the palladium in microchips all trace their origins to these violent encounters. The cosmos literally rearranges itself in death to birth the ingredients of civilization. Now imagine harnessing that power. While we can't replicate neutron star conditions on Earth, we're already borrowing their tricks. Experimental reactors use particle accelerators to simulate rapid neutron capture, producing medical isotopes for cancer treatment. Some physicists theorize that future fusion plants might tap into similar high-density energy states, using magnetic confinement to mimic the extreme pressures found in stellar collisions. More radically, a concept called quantum vacuum propulsion envisions extracting energy from space-time distortions, the very ripples LIGO detects, potentially enabling engine systems that ride gravitational waves like surfers on a cosmic tide. The challenges are as staggering as the rewards. Neutron star material is so dense, a sugar cube-sized sample would weigh as much as Mount Everest. Containing even microscopic amounts would require magnetic fields rivaling those of the stars themselves. Yet labs like CERN are edging closer, with antimatter traps and quark-gluon plasma experiments revealing how matter behaves under neutron star-like extremes. Private ventures are also joining the race. One startup aims to synthesize rare elements by bombarding heavy metals with neutron beams, a terrestrial echo of cosmic alchemy. Beyond practical applications, studying these processes reshapes our cosmic perspective. Neutron stars remind us that destruction and creation are two sides of the same coin. A supernova's death throes become the raw materials for new planets. Future telescopes like the Vera Rubin Observatory will scan for merger remnants, mapping how these events seed galaxies with life's building blocks. Meanwhile, projects like the Einstein Telescope, a next-gen gravitational wave detector, will listen for collisions deeper in space, potentially uncovering new element-forming reactions. The ultimate dream, capturing the energy of a neutron star merger itself. While we're millennia from such feats, the theoretical framework exists. A single merger emits more energy in seconds than all the stars in the observable universe combined, enough to power human civilization for billions of years. Concepts like Dyson-Harrop satellites propose beaming energy from cosmic events using electromagnetic fields, turning celestial cataclysms into renewable resources. It's the pinnacle of human ingenuity, learning to thrive not just despite the universe's violence, but because of it. This duality, neutron stars as both destroyers and creators, mirrors humanity's own journey. We've turned deadly radiation into cancer treatments, volcanic heat into geothermal energy, and now stand poised to harness the very forces that once threatened our existence. The cosmos doesn't deal in pure danger or pure bounty. It offers raw materials for those bold enough to reshape them. And somewhere in that endless cycle of collapse and rebirth lies the secret to our future among the stars. Imagine a civilization so advanced, it treats neutron stars not as cosmic hazards, but as power plants. While this sounds like science fiction, the sheer energy output of these stellar remnants makes them irresistible targets for theoretical futurists. A single magnetar flare releases more energy in a millisecond than humanity has consumed in its entire history. And some scientists speculate that harnessing even a fraction of that could propel our species into a Kardashev Type 2 civilization, capable of utilizing all the energy from its host star. The concept isn't entirely far-fetched. Just as dams capture the kinetic energy of flowing water, futuristic Dyson-Harrop satellites could theoretically tap into the relativistic particle winds and magnetic fields streaming from neutron stars, converting them into usable power through quantum vacuum effects or superconducting loops. The engineering challenges are, of course, astronomical. Constructing infrastructure near a neutron star would require materials that don't yet exist, substances capable of withstanding gravitational forces strong enough to spaghettify a human at 1,000 miles away, and magnetic fields that could rip apart atomic bonds. Even getting close presents problems, the intense radiation environment would fry conventional electronics within seconds. Yet physicists like Dr. Andreas Hein of the Initiative for Interstellar Studies suggest that breakthroughs in quantum shielding or self-repairing nanomaterials might one day make the impossible merely difficult. His team's stellar engine concepts propose using neutron stars as galactic waypoints, their energy beams acting as propulsion for interstellar arcs on millennia-long voyages. What makes these speculations more than just futuristic daydreams is how they force us to rethink energy itself. On Earth, we're constrained by chemical reactions and nuclear fission, but neutron stars operate on a scale where matter and energy blur. Their magnetic fields can accelerate particles to 99.9% light speed, creating natural particle accelerators far more powerful than anything at CERN. Hypothetical extraction methods range from orbital scoops, capturing relativistic jets, to space-time altering devices that siphon energy from the star's rotation, a process analogous to how black holes lose spin through Penrose processes. The common thread: these ideas all exploit fundamental physics rather than violating it, making them tantalizingly plausible given enough technological maturity. Beyond raw power, neutron stars could serve as cosmic laboratories. Their extreme densities create states of matter impossible to replicate on Earth: hyperons, quark-gluon plasmas, and possibly entirely new phases of material. Harvesting even microscopic samples could revolutionize energy storage, yielding batteries with energy densities millions of times greater than lithium-ion. Some theorists even propose that compressed neutronium, the exotic matter in neutron star cores, might enable warp drive concepts by generating localized spacetime distortions. While firmly in the realm of conjecture, such possibilities highlight how studying these stars isn't just about avoiding their dangers, but potentially unlocking their gifts. This shifts the narrative from survival to transcendence. For millennia, humanity has adapted to nature's whims, but the ultimate adaptation might involve bending cosmic forces to our will. The same magnetic fields that threaten satellites could one day propel starships. The gamma rays that ionize our atmosphere might power cities. It's a perspective that transforms neutron stars from distant curiosities into keys to humanity's cosmic destiny. And that's the true power of these thought experiments, not that they provide blueprints, but that they expand our vision of what's possible in a universe teeming with energy waiting to be understood. Which brings us to the profound question underlying all these speculations. What does our fascination with harnessing neutron stars say about humanity's place in the cosmos? We're a species that gazes at stellar corpses and sees not just obstacles, but opportunities, a testament to our unique blend of curiosity and ambition. Whether we ever tap into these cosmic powerhouses is almost beside the point. The mere act of contemplating it redefines our relationship with the universe, from passive observers to active participants in a grand cosmic story still being written. After all, the stars that once terrified our ancestors are the same ones that now inspire our boldest dreams. And in that tension between fear and wonder lies the essence of exploration itself. Humanity's place in the cosmos is both humbling and electrifying, a paradox where vulnerability meets boundless curiosity. The idea that a stellar corpse millions of light years away could momentarily rattle Earth's magnetic field isn't just a scientific curiosity. It's a cosmic reminder that we're not passive observers of the universe, but active participants in its grand, often turbulent narrative. This revelation sparks a duality within us, the sobering awareness of our fragility, paired with the exhilarating drive to decode the very forces that shape our existence. Consider the broader implications. For centuries, humans saw the heavens as static, a predictable clockwork of stars and planets. Today, we know the cosmos thrums with volatility. Stars explode, black holes collide, and magnetars unleash bursts of energy that could, under the right conditions, ripple through our technology and skies. Yet this instability isn't cause for despair. It's an invitation to innovate. Every solar storm weathered, every magnetic anomaly studied, sharpens our ability to adapt. The same cosmic violence that threatens also forges the elements we rely on, from the iron in our blood to the silicon in our computers. Destruction and creation are two sides of the same celestial coin. This duality extends to how we perceive risk. A magnetar's outburst is vanishingly rare, but its mere possibility reshapes our priorities. It drives nations to harden power grids, inspires engineers to design radiation-proof satellites, and fuels international collaborations to monitor the skies. In confronting these cosmic wild cards, humanity displays its most resilient trait: the ability to transform existential threats into catalysts for progress. The same curiosity that once mapped constellations now builds early warning systems, proving that understanding the universe isn't just about survival, it's about evolving alongside it. Yet beyond practical preparations lies a deeper, almost philosophical shift. Recognizing Earth's vulnerability to distant stellar events dissolves the illusion of isolation. We're not a sheltered oasis adrift in a quiet void. We're woven into a dynamic web of gravitational tides and magnetic filaments. When a neutron star's flare brushes our atmosphere, it's a tangible thread connecting us to the cosmos's heartbeat. This interconnectedness fuels scientific wonder, but also artistic expression. Poets and painters have long drawn inspiration from auroras, those shimmering reminders of Earth's dialogue with space. The key takeaway isn't fear, but perspective. Neutron stars teach us that the universe operates on scales of energy and time far beyond human experience, yet we've developed the tools to eavesdrop on its whispers. From ice cores preserving ancient radiation spikes to algorithms predicting stellar outbursts, each discovery tightens our grasp on the cosmos's rhythms. And while we may never control these forces, we're learning to anticipate them, coexist with them, even harness their lessons. So where does that leave us? Not as passive victims of celestial chaos, but as a species uniquely equipped to dance with the universe's volatility. The same magnetic field that a dead star might disrupt also cradles our atmosphere, enabling life to flourish. The same gamma rays that threaten satellites once forged the atoms in our bones. This interplay of peril and wonder defines our cosmic address, a testament to resilience written in the language of physics and starlight. The universe may be indifferent to our existence, but it's far from indifferent to our curiosity. And that's a story still being written, one observation at a time. From the violent birth of neutron stars to their eerie ability to reach across the cosmos and nudge Earth's magnetic shield, we've uncovered one of space's most extraordinary paradoxes: how the remnants of dead stars can shape the destiny of living worlds. While the odds of a catastrophic magnetar outburst striking Earth are astronomically low, history reminds us that improbable doesn't mean impossible. The 774 AD radiation spike preserved in tree rings and the unsettling disruptions from distant flares prove these cosmic whispers can touch us, even from halfway across the galaxy. But this isn't a story of doom. It's a testament to human ingenuity. Every flicker of gamma rays we detect, every simulation of magnetic chaos we run, sharpens our ability to coexist with the universe's volatility. We've transformed from passive observers to active interpreters of cosmic signals, building early warning systems that blend cutting-edge astrophysics with global cooperation. The same neutron stars that once sparked ancient myths now inspire international research initiatives, proving that curiosity is our greatest shield against the unknown. What makes this journey so remarkable isn't just the science, it's the perspective shift. These stellar ghosts force us to confront a humbling truth. Earth's magnetic field, for all its might, is just a fragile bubble in a cosmos teeming with invisible forces. Yet within that fragility lies resilience. Life has weathered magnetic reversals and cosmic bombardments before, adapting to every challenge the universe has thrown its way. Now, as a species wielding technology, we're learning to do the same, not by resisting the cosmos, but by understanding its rhythms. So as we gaze at the night sky, let's marvel at neutron stars not just as distant curiosities, but as cosmic teachers. Their extremes push the boundaries of physics, their outbursts remind us of our interconnectedness, and their very existence proves that destruction and creation are intertwined. The universe doesn't deal in pure danger or pure bounty. It offers raw materials for those bold enough to study them. What's your take on these celestial wild cards? Have we underestimated their potential, or are we giving them too much cosmic credit? Drop your thoughts below. And if you've ever wondered what other space mysteries might be lurking just beyond our detection, hit subscribe. We're just getting started unraveling the universe's greatest secrets. Until next time, keep looking up, but maybe keep an eye on your